important SLOOH team member and SLOOH specialist. Dr. Bover is our director of curriculum. So all of the quests that you see have been created by John himself. So very important member of the team, and I'll pass it over to him to give you guys a little presentation.
Thank you so much, Anna. Welcome, everybody. I'm so glad that you're all here and happy to talk with you all today. We are going to go over a little presentation that I've created called The Fate of the Sun. And so I'm going to share my screen here and go ahead and make sure that you're taking a look at the screen. And um, if you have any questions throughout the presentation, feel free to drop them in the chat. Do we have yeah, go ahead and drop them in the chat. And so what I originally had planned for us was a journey through space using our live telescopes. But unfortunately, and I'll even show you if I scroll down here a little bit, there's a bunch of missions that I scheduled on my fancy account. But unfortunately, you can see that my missions aren't running due to the weather. And this is what happens sometimes with when you're using the live telescopes is the weather happens and we're not able to see into space. But luckily, I still have a presentation that we're going to go through together. And we're going to learn about the four different kinds of nebulae in the universe, the two different kinds of star clusters that are in the universe, and what happens at different stages of stellar evolution. I'm also going to talk a little bit about how SLOOH processes their images robotically, how they go from being a black and white image to being a beautiful color image that we've been sharing already in the chat today. Towards the end, I'm going to give you I'm going to suggest two quests for you to start as well. So, we're going to go through a journey, not across space, not just across space, but across time. So, we're going to see seven incredible objects in the southern sky that are glowing clouds of gas, blazing stellar nurseries, ancient star cities packed with millions of suns. And at the very end, I'm going to show you a glimpse of what our own star is going to look like 5 billion years from now. So tonight's theme is the fate of the sun. And the question I want you to hold all afternoon is what happens to a star when it runs out of fuel? But to answer that, we have to start at the very beginning. And the very beginning is very, very dark. So the first object we're going to look at is called the Dark Nebula or Barnard 93. So this is a region in space that's in the Sagittarius constellation. It's about 10,000 light years from Earth. And what you're looking at may seem like nothing. It looks like there's an absence of stars right here where my mouse pointer is. We can all see my mouse pointer, right? Give me somebody please give me a confirmation you can see my mouse pointer.
Yes.
Yes.
Thank you so much. So this is the Dark Comet Nebula, sometimes called Barnard 93, and it's a cloud of gas and dust so thick and dense that it blocks light from everything behind it. So it's almost like a cosmic fog bank. We can see a bunch of stars scattered all around it, but in the middle here, a darkness. And again, it's what I want you to understand about these dark nebulae. The darkness is not empty. Deep inside that cloud, stars are forming. Gravity is slowly pulling together gas and dust into clumps inside of this cloud, and those clumps are heating up. Over hundreds of thousands of years, these clumps will collapse, ignite, and become stars, just like our sun. And when I say ignite, I mean something very specific. The core of these clumps, once they get hot enough, which is about 10 million degrees Celsius, hydrogen atoms that are there begin smashing into each other, infusing together, and creating helium atoms. And in that nuclear reaction process releases an enormous amount of energy as light and heat. And that's what a star actually is, a giant ball of gas held together by gravity, powered by fusion in the core. Um, and so that's what is happening in the center of our sun. This is the sun taken just today with SLOOH's Canary 5 solar telescope. And in the center of the sun, fusion process is naturally occurring and it's converting hydrogen atoms into helium atoms and releasing an enormous amount of energy that eventually makes its way to the surface of the sun, out into space, and that's the light that we end up seeing. And so stars can keep burning this hydrogen for billions of years as long as there's hydrogen fuel left in their cores. So this is how our star was born 4.6 billion years ago. It started as a cold, dark clump inside of a cloud, just like this one. Now, these dark nebulae, they're mostly made of hydrogen gas mixed with tiny dust particles that are really smaller than the width of human hair. And the temperatures inside of these nebulae, not inside the clumps, but inside the cloud itself, is incredibly cold. It's about minus 260 degrees Celsius, which is about negative 436 degrees Fahrenheit. It's very close to what's called absolute zero, which at that temperature, absolute zero, all molecular and atomic motion stops. And so stars end up taking take millions to hundreds of millions of years to fully form inside clouds like this one. And this particular one, like I said, it was 10,000 light years from Earth. It's about 44 light years long and about 6 light years wide. And so when you're looking at a dark nebulae, you're seeing a place where stars are being born, a cosmic nursery. And somewhere in there, billions of years from now, a star not unlike the sun is coming to life. So I want to move on to the next stage. So what happens when stars begin forming in the nebulae? Well, when these young stars first switch on, the first thing they do is start lighting up the cloud around them. But here's the thing. In these early stages, a newborn star isn't hot enough or powerful enough to actually change the gas that's around it. They can't ionize any of the hydrogen gas or energize it yet. It can't make it glow on its own. All it can do is release some of its light, and the dust within that cloud is going and that light is going to bounce off of the dust within that cloud. And that's what in a reflection nebula is. A cloud that doesn't generate its own light, instead, it scatters or reflects light from nearby stars. So kind of like how dust particles in foggy air scatters beams from a flashlight here on Earth. It glows, but it's not because it's emitting its own light, it's borrowing light from somewhere else. And so this object that we're looking at here, this is called the R Coronae Australis complex, or the RCRA for short. It's in the constellation Corona Australis, the Southern Crown, and it's one of the closest star-forming regions to Earth. It's only about 430 light years from Earth. And the stars inside of it are incredibly young. They're only a few million years old, still nestled in the cloud that they were born in. And so when we look at this reflection nebula, we can see a lot of dark nebula features. There's still a lot of stars that are being blocked. There's still a cloud that's blocking starlight behind this nebula. But inside here, we can see these two stars and some of the stars here. These are newborn stars. And you can see wisps that are nearby them. That's the reflection nebula part. So these stars are just now starting to turn on. Reflection nebula tend to look blue, and it's for the same reason that the Earth's sky is blue. Dust ends up reflecting short blue wavelengths more effectively than it does longer red light ones. So, what happens is light from the sun ends up hitting the atmosphere and it scatters or reflects the blue light more than it does the red light. And so that's why the sky ends up being blue during the day. It's actually scattered sunlight. So you can think of reflection nebulae and the RCRA nebula as being a slightly later snapshot compared to the dark comet nebula. So in dark nebula, the stars haven't really switched on yet, but here they just ignited and their light is starting to spill out into the surrounding cloud. Now, it would be really cool to see our sun in something like this 4.6 billion years ago. And then after this, Well, does anybody have any questions so far? I'm looking through the chat. I don't see any questions
I
yet.
think there's one over here by Sib.
Let's
Can you go to the
see.
first line?
This one here?
Yeah. So I actually have one of these pictures in my photos in SLOOH.
Awesome. That's great. You'll be able to use it in one of the quests that I'm going to be letting you all know about later on.
Yeah, I'm now, yeah.
Do you have a question about this one?
I'm just telling you I have a photo.
Oh, cool. Well, that's great. I'm glad that you were able to get this one. You can see how why they call it the Dark Comet Nebula. It kind of looks like a nebula wisp in the sky. All right, so let's move on to when the stars are starting to really release their light into the surrounding nebula. And so a reflection nebula shows us that quiet early stage of star formation, young stars just barely lighting up the cloud around them. But when the stars grow more massive, the energy blasting out of these newborn stars starts heating up the gas around them. And when that gas actually gets hot enough and powerful enough, their light doesn't just scatter off of the dust, it actually tears the hydrogen gas apart, atom by atom, and makes those hydrogen atoms glow. And that's what an emission nebula is, a cloud of gas that's lit up from the inside by the energy of the stars within it. And so the one we're looking at right now, this is probably the most impressive emission nebula in the entire sky. It's called the Tarantula Nebula, or NGC 2070. It's named for its long, spidery tendrils of glowing hot gas that kind of looks like tarantula legs. And it's located inside the Large Magellanic Cloud, which is not inside the Milky Way galaxy. It's inside a small satellite galaxy orbiting our Milky Way. It's about 160,000 light years away. Now, the thing about light years is a light year is a distance unit. It describes how far that light would travel in 1 year. So when we're looking at something 160,000 light years away, we're looking at light that left the Tarantula Nebula roughly 160,000 years ago. And that's long before the first cities, before writing, before humans started doing agriculture even. Our ancestors were just small bands of hunter-gatherers who hadn't seen the wheel yet when the light from the Tarantula Nebula left. And the Tarantula Nebula is actually really, really big. It's about 1,000 light years across. It's one of the largest known emission nebulae that we see in the sky. At its core, there's a star cluster there called R136, and it contains some of the most massive stars ever discovered. Some of them are over 150 times more massive than our sun. What's also really impressive about this one is if the Tarantula Nebula were as close to us as one of the more famous mission nebulae in the sky, the Orion Nebula, which is about 1,400 light years away, then the Tarantula Nebula would be bright enough to cast shadows during the night. That would be pretty cool. Um, I see there's a hand up. Do you have a question?
Yes, I have
Oh,
a question. In SLOOH, some of the like things you can't like really take photos of because it doesn't let you. So like, why doesn't it let you do that?
well, when you're looking at the live telescopes, you mean, or?
Yeah, when you're looking at the telescopes, I can post a screenshot of one which is not there on the chat.
Yeah, go ahead and post that screenshot. And while you're posting that screenshot, I want to mention that these different pinks and reds that you see in emission nebula, these are coming from hydrogen gas that are being excited or energized by the light from these newborn stars. And it works really the same way that a neon sign glows that you may have seen in like a restaurant window, for example. When you heat up when you heat up atoms to a particular when you heat up atoms inside of a gas tube, that those atoms will eventually glow and give off certain wavelengths of light. And that's what's happening here. The atoms within the nebula are being energized by the young stars, and they're causing it to glow. Now, Sabrina just posted an image of she said Carina Nebula, but this image that she posted is actually of the Tarantula Nebula. This is from James Webb Space Telescope, and that little triangle that you're seeing there is actually this little triangle that I have my mouse pointer going around. So the JWST can see in a slightly different wavelength region than what SLOOH telescopes are. SLOOH telescopes looks at what's called optical wavelengths that we can see with our eyes. But JWST can see in the infrared, and so it's able to see some of the dust that's within these nebulae. So a thing about these images, SLOOH automatically processes the images as they're coming in. And so the telescopes, it captures data in optical wavelengths. And so this is a graph that's showing different wavelengths in the bottom here. And SLOOH first starts off capturing wavelengths in all of the optical region. And then it changes and adds a filter on the telescope, and it's able to capture a bunch of light that's just in the blue side of the optical wavelengths. And then it changes to another filter, and it captures just the green light from what it's looking at. And then it changes the filters one more time, and it captures just the red light coming from the objects. And then it processes those images and stacks them together to create a color image. So I want to give you another example of what an emission nebula looks like. This one's called the Trifid Nebula. And this image was also taken with the Australia 1 half-meter telescope. In fact, all the images we've seen thus far have been from Australia 1 half-meter telescope, with the exception of the sun. That one was with SLOOH's Canary 5 solar telescope. And so initially, the when you first look at a live mission, it's going to look black and white. And this is the telescope taking in all of the wavelengths of light in the optical spectrum. But then after it captures blue light, just the blue light from the objects, just the green light from the objects, and just the red light from the objects, it's able to stack these images together and create a beautiful color image. Now, the Trifid Nebula is really cool because this red globule that you see in the bottom here, this is from hydrogen atoms that are energized. And when hydrogen emits its own light after being energized, it's this reddish color. But on top here, you can see this small blue cloud. This is basically a reflection nebula. It's light that's being the blue is dust within this nebula that the light with the starlight inside is scattering off of. So the Trifid Nebula, you kind of get two nebulae in one. You get an emission nebula in the bottom, and you get a reflection nebula in the top. Now, Arab posted a image of the Eagle Nebula in the chat, and you can see how all of the red that's coming from the Eagle Nebula, that's from energized hydrogen gas that these hot newborn stars are emitting. Very cool. So we've seen three types of nebulae now: a dark nebula, a reflection nebula, and an emission nebula. Now, up next, I want to show what happens when the hydrogen gas finally clears and the stars start scattering out into space. So this is an open star cluster. And just looking at the chat. So over millions of years, the stars forming inside of a nebula slowly push away the gas and dust around them through radiation and through stellar winds. But the real cleanup crew in emission nebulae is when the most massive blue stars in the cluster die. These massive blue stars they burn so hot and so fast that they exhaust all of their fuel in just a few million years. The sun's lifetime, for example, is 10 billion years, but the hot blue stars only live millions of years, with a flash in the pan of in cosmic time. And when those hot blue stars in their lives, they explode as what's called a supernova. And this it releases an immense amount of radiation and energy. Often these supernovae outshine entire galaxies. And so when we look at other galaxies, we can see blue stars exploding in them, going supernova, because it ends up being a bright dot that we see in the galaxies. And a lot of folks end up seeing those on SLOOH too, which is really cool. But when these supernovae happen, it blasts the remaining hydrogen gas out of the cluster entirely. The cloud ends up dispersing, and what's left behind is a loose group of stars. All of these stars are roughly the same age. They were all born in the same cloud, and they spread out across space together. And this is what an open star cluster is. Probably the most famous open star cluster in the sky is called the Pleiades, and it just recently got back into the night sky. And so you were able to snap some
I just
images
took a
and go
picture
on.
of the Pleiades like a few days ago.
Awesome. Awesome. So it's a very impressive one. So this one is from the SLOOH's Canary 3 Deep Sky Telescope. It's the only telescope that has a field of view big enough to actually capture the whole thing. So if you want to get some Pleiades images, make sure to use Canary 3 for that one. Yes, you have a question.
Yeah. I I took a photo of the Sagittarius star cloud before.
Oh, that's great. That's another really awesome cloud of stars. So these this is the Pleiades. It's also known as the Seven Sisters. It's the closest and perhaps the most famous open cluster in the sky. It's only about 440 light years away from Earth. It's in the constellation Taurus. What's really cool about the Pleiades is when it's out in the night sky, you can actually see it with your naked eye. And cameras on phones are good enough now where if you take a picture of the Pleiades, you can actually see some of the five brightest stars within it. These ones here. And practically every civilization can see the Pleiades in the sky, and everybody has like their own stories associated with the Pleiades, which is really cool to think about. Now, the Pleiades cluster has about 1,000 stars in it. It's 350 to 400 light years across. Oh, it's a typo there, 43 light years across. And over hundreds of millions of years, these stars are going to slowly drift away from each other. So right now, this star cluster is relatively young. It's about 100 million years old. But in about 250 million years from now, the Pleiades is going to drift apart so much that the stars are going to be dissolved into the rest of the galaxy. One thing that's really neat to see, and the Pleiades is a really good one to see these effects. You can see a little bit of clouds surrounding some of the more brighter stars. That's still leftover dust from its nebula stage. And so not every star cluster you'll be able to see some of this leftover dust, leftover nebulosity, as we would say in astronomy. But some of them can, and the Pleiades is a very beautiful one to see this. So eventually these stars are going to go off on their own. And but even though they'll be on their own, they're still going to be moving in the same direction as they orbit around the center of the galaxy. And what's really neat is the Big Dipper is also a dispersed open star cluster. It's called the Ursa Major Moving Group. Five of the seven stars in the Big Dipper were born together in the same cloud, and they're all drifting through space as a family. They're all about 80 light years away. So it's spread out so much that it no longer looks like a cluster, but that shared motion kind of gives the story away that they were all born in the same nebula. And so there's actually a quest called the Starry Night over the Rhone where you can learn more about the Ursa Major moving group. But that's not one of the two quests that I was going to suggest us go on tonight. But you can go on that one and finish it because the Big Dipper is available right now in the sky to see. So our sun was born in a star cluster just like this one. About 4.6 billion years ago, the sun formed inside of a nebula alongside thousands of sibling stars. Those siblings drifted apart over millions of years, scattered by the gravity within our galaxy. And today, the sun's birth cluster is completely gone. The sun has been traveling alone through the galaxy ever since. But somewhere out there, the sun has siblings. And scientists have found some likely candidate stars that have the same chemical footprint and are and some of the same galactic history that the sun is. But we can't say for sure what now. But our birth cluster is long gone. So, do we have any other questions at this point before we move on? No more questions. All right, well, let's move on. There's another kind of star cluster that I want to introduce you to, and this one is called a globular star cluster. So, open star clusters are young and loose clusters of stars, born recently, slowly drifting apart because there's not enough stars, not enough mass in stars to hold or keep all of those stars together. But what I want to show you here is something completely different. This is a kind of star cluster that's ancient, massive, and tightly packed together that it looks like a single glowing ball of light from a distance. This is what's called a globular cluster. And the one we're looking at right now is one of the greatest ones in the sky. It's called 47 Tucani, or NGC 104. It's quite a distance away from Earth. It's within the Milky Way galaxy. It's 1,300 light years away. And this star cluster contains roughly 2 million stars in it. And it's packed into a sphere that's only 120 light years across. Now, if we go back to the Pleiades is only 43 light years across. And so these two star clusters are almost relative, especially in astronomical terms, they're roughly the same size. Uh, and the Pleiades only had 1,000 stars in it, but the 47 Tucani has 2 million stars in it. There's so many stars in globular star clusters that the gravity prevents these stars from drifting off away and going on into the galaxy on their own. And this cluster is very old. It's 13 billion years old. It's almost as old as the universe itself. The universe is about 13.8 billion years old. So these are very old sites of where star formation occurred. And so if any of the stars had any planets around them, the night sky would be brighter than anything we would see on Earth because of the sheer amount of stars there. And what's really interesting about globular star clusters is where they are in the Milky Way. The Milky Way galaxy we typically think of as being a disk of stars and gas that are orbiting around the common center. But globular clusters, they don't orbit in that disk of the Milky Way. They orbit above and below the disk, and they form a spherical, what we call halo. And so these globular star clusters, they pass through the disk of the galaxy over the million years that it takes them to orbit around the center of the galaxy. So as I mentioned, the 47 Tucani is only 120 light years across, and that's not very different from the span of some of the large open star clusters. So open star clusters only contain a few thousand stars, and globular star clusters contain millions of stars. So they're about the same footprint, but they're completely different densities of stars, which is the number of stars per area. And so if you think of open star clusters as being small towns, globular star clusters are like mega cities of stars. So why did the early universe make such vastly bigger star clusters than the nebula we saw tonight? Well, it comes down to the available gas that's around in these different parts of the universe's history. Oh, we just posted a globular star cluster M107, and you can see here too, it's a spherical cluster of stars. Oh, and another one of the camp members said that they have an Omega Centauri cluster, and if you have that one, go ahead and post that one in the chat too. That one's another beautiful one, and you can see that they all kind of have the same visible structure. They're all symmetrical, a big ball of gas. There's the Omega Centauri cluster. So cool. And with the color that we can see there's a lot of different star colors here, but we don't see any blue. And it's because all of the blue stars, they've already gone supernova. So the only ones that are left behind are white stars, orange stars, red stars. That's really neat.
Also blue stragglers.
That's right. Whoever said that, you are totally right. So there are
Like
these,
basically, there's these giant hot blue stars that shouldn't be existing.
well, those hot blue stars, they're not stars that were around when all of these stars formed. What ended up happening is
Like
there
they
were multiple
collided.
stars that collided together and they formed like a new giant big blue star. That's right. Yeah, and that's what the blue stragglers are. They're really cool when you can see some of them. And there are some globular clusters on SLOOH that if you look at the color images, you can see those blue stragglers. That's very awesome to bring up those guys. Um, so these globular star clusters, they're very symmetric. They look like a big ball versus the open star clusters. They're not symmetric. They're kind of amorphous. They can be in different shapes from one another. Um, and so that's one of the differences between open star clusters and globular star clusters. Another is the number of stars within them. Open star clusters have on of order thousands, maybe 10,000 stars in them, versus globular star clusters that have millions of stars in them. And then there's the stellar density. There's way more stars per like light year chunk in globular clusters than there are in open star clusters. So again, why did the early universe make these massively bigger clusters of stars than from the nebulae that we were just looking at that created the open star clusters? And it comes down to gas. The early universe had a far richer in raw hydrogen and helium than it is today. So if you think about it, when the universe first formed, there weren't any stars at all. In fact, most of the universe was just hydrogen gas, a little bit of helium, some other trace elements. There was already dark matter around, kind of forming into different clumps that would eventually become the first galaxies, but there wasn't any stars. It was just a sea of hydrogen gas that gravity started pulling together and creating stars. So these enormous clouds hadn't yet been consumed by earlier generations of stars. Those giant gas reservoirs collapsed all at once, forming millions of stars in a single event, rather than the thousands of stars we see coming out of modern nebula like the Tarantula Nebula. Uh, So the ingredients were the same, but the supply was almost incomprehensibly larger. So the globular clusters are what star formation looks like when the universe has a lot of gas to work with. There it is. Oh, wait. All right, see, I had some other information that I wanted to let you all know. I need to find my Well, in any case, globular clusters, they're not a part of the star formation story we've been telling tonight. There's something much older. They're relics from a very early universe formed in a single violent burst of star formation billions of years before our sun existed. And they've been holding together ever since, a permanent city of stars, glued together by gravity. So, do we have any questions about open star clusters or globular star clusters before we move on? All right, well, let's move on to the next section. We're going to talk about planetary nebulae. So we've been on a journey today. We started in a dark nebula where stars are born. We saw the first light of newborn stars scattering through the dust in a reflection nebula. We saw massive stars tearing through an emission nebula and causing that nebula to glow. We also saw stars emerge from their nebula as a young open star cluster, just like the one our sun was born in. And we visited an ancient star city 13 billion years ago when we looked at the globular star cluster. And now we arrive at the end of the road, at least for a star like the sun. When a star like the sun eventually runs out of hydrogen fuel, which is going to happen in about 5 billion years from now, it doesn't explode. It doesn't go supernova like the big bright blue stars do. It doesn't collapse into a black hole or a neutron star, which those big blue stars that went supernova end up doing. But something quieter and perhaps stranger happens. First, the star starts swelling into a red giant star. Without there being without there being any hydrogen fusion going on in the center of the star starts to collapse on itself and it starts to heat up the helium that's in the core, and the helium starts to do a fusion process to combine into carbon and oxygen. And this starts the star swelling up and getting bigger and swallowing the inner planets whole. So gravity pulls the star inward, heating up its core, shifting it into burning helium, the ash that's left over from the billions of years of hydrogen fusion, turning it into carbon and oxygen deep in the core. But this extra fusion energy causes the star to swell up and growing even larger than before. But when the star swells up, it gets cold and it changes color. It turns red. This is called a red giant. And so at some point, something remarkable happens. The star starts to pulsate. It expands outward, it gets cold, and then gravity stops that expansion and it causes the star layers to collapse again. And this causes some of the helium in the core to fuse again, which creates energy that causes the star to swell out. And so the star kind of beats almost like a heart. They're called Mira variables, and we've seen them. They're sun-like stars that are in their final act. And with every pulse that these red giant stars go through, the star sheds more and more of its outer layers into space. So eventually, the outer part of the star is going to be released out into space. And what's left over is the exposed core of the star. This dense, incredibly hot ball of carbon and oxygen the star has spent its life making. And this is what's called a white dwarf. It's a slowly cooling core of a star that's fading over billions of years. And in this one here, the outer layers of star that are drifting outwards into space, they're lit up by the white dwarf's fierce heat. Because these white dwarfs, they emit UV radiation and they form a glowing shell around this dying core. And that glowing shell is what the planetary nebula is. So here, this is called the Helix Nebula. It's 255 light years from Earth. In the center of the Helix Nebula is a white dwarf. And this white dwarf is several tens of times hotter than the surface of the sun. Typically, well, in the for the Helix Nebula in particular, the core is about 20 times hotter than the surface of the sun. And so this is emitting a lot of UV radiation and it's causing the star layers to glow. And it's very similar to emission nebulae. Emission nebulae are glowing because the hot blue stars are energizing the hydrogen gas that's within the nebula. Here, the light from the hot white dwarf is causing not only the hydrogen to glow, but the other elements that are inside the star too. As all stars, at least second and third and fourth generation stars, they end up having a little trace elements of other atoms within them as well. And so this is the Helix Nebula. It's inside the constellation Aquarius. It's sometimes called the Eye of God, if you've ever heard of that before. And when you see it, you can kind of understand why. It's a vast glowing ring that's staring back at you from the darkness. It's one of the closest planetary nebula from Earth. Like I mentioned, it's only 255 light years away. This particular capture was done with SLOOH's Canary 1 half-meter telescope. Definitely recommend using that telescope if you want to capture the Helix Nebula. And though the nebula it looks like it's circular in shape, but these are three-dimensional structures. It's kind of more shaped like a barrel or tube with one end kind of pointing directly at us. Now, even though this is called a planetary nebulae don't have anything to do with planets. They come from when these were first seen in the
Yeah,
telescopes.
and then they thought there were planets.
Yeah, they kind of looked like planets. They were about the same size as Saturn, so they ended up calling them planetary nebula.
I
I
have a
see.
I have a comment. When you were talking about dark nebula, I forgot to say this, but I have a mission to a dark nebula called the Snake Nebula.
That the Snake Nebula is probably my favorite dark nebula. So I'm excited for you to get that one and take a look at it and see if you can see the snake. It's really impressive.
Okay.
So I want you to think about when you're looking at this planetary nebula, in any planetary nebula, think about how 5 billion years from now, the sun is going to look like one of these. The sun is going to swell into a red giant, swallow Mercury and Venus, scorch the Earth beyond recognition. Then it's going to continue shedding its outer layers, and it's going to leave behind a glowing shell, just like the Helix Nebula, with a tiny white dwarf cooling quietly in the center. Now, what's really amazing is this material from the planetary nebula continues to go off into space. And that material eventually meets other planetary nebula material, and they're going to form massive clouds of gas. And eventually, it's going to cause this whole process to begin again. All of this gas is going to eventually turn into a dark nebula, and it's going to collapse, and it's going to make new stars. So the atoms that are within your body were really forged in stars that ended exactly like this. So we're looking not only at the past, but we're also looking at the future of the stars that make your life possible. And in fact, there have been six other stars that had to exist before the sun in order to make the atoms that are within our bodies and surrounding us here on Earth. There was a binary high mass star. There are binary high mass stars that had to end their lives. This is two stars that are high mass, and those end up generating things like gold that we see on Earth. And then after that, we needed a binary low mass stars to end their lives to create all of the iron that we see around us. But we also needed an isolated low mass stars to make carbon, and we needed isolated high mass stars to make a bunch of oxygen. And so if it wasn't for all of these stars forming and going through their life cycles, we wouldn't have had all of the atoms necessary that we need today for our life. So let's run through again what we went through tonight. We followed the story of star formation. A dark nebula, we look at the dark comet nebula, a cold dark cloud where stars are born in silence. We looked at a reflection nebula, the RCRA complex, where newborn stars' light first scattered through the dust around it. We looked at an emission nebula, the Tarantula Nebula, where hot stars are blasting the surrounding gas until it glows. We then looked at an open star cluster, the Pleiades, where stars are emerging from the nebula, just like a cluster where our sun was born. We looked at a globular star cluster, 47 Tucani, a 13 billion year old city of 2 million stars. And we looked at a planetary nebula, the Helix Nebula, which is the future of our sun 5 billion years from now. So all of these images that we looked at tonight are things that you could schedule on SLOOH to capture your own images of to use in different quests or to share with everybody like we're sharing in the chat. I want to introduce you to a couple of quests and then I want to show you how to schedule a mission in one of those quests. But before we do that, I want to open the floor for any additional questions that you may have. All right, well, it doesn't look like we have any additional questions. The things that we've been looking at tonight, the four kinds of nebulae and the two kinds of star clusters, you can use in the Survey the Nebula quest and in the Examining Star Clusters quest. So these are two quests that I suggest that when you have your SLOOH time, when you're working on your own on your accounts, go ahead and start and do these quests. They're a lot of fun. And at the end of these quests, you'll be able to generate a poster that showcases your objects that you captured. This is an example of the posters that I generated when I went on the Survey the Nebula quest and the Examining Star Clusters quest. Now, one of the camp members, I'm not sure who was saying it, but they were saying that they scheduled a mission to the Snake Nebula. Here's the Snake Nebula here, and you can see the dark cloud where stars are forming with inside. That definitely looks like a snake. So I want to show you how to get to these quests. So when you're on the dashboard, you want to click on, and your navigation bar might actually be on the top of the screen. There's a shield that looks like, how do I get this thing pop out? A shield that says quests. When you click on that, it'll bring you to a page where you can see the quests that you're working on right now. But then in the center, there's this button that says All Quests. If you click on All Quests, that brings you to a page that looks like this. So if you search for Examining Star Clusters, you'll see the Examining Star Cluster quest pop up. Or if you search for Survey the Nebula, you'll see the Survey the Nebulae quest. So you click on Survey the Nebulae, it brings you to a quest overview page, and there'll be a button that says Start Quest. When you hit Start Quest, it's going to bring you to the first step of the quest that looks like this. There is an introduction for you to read through and kind of get acclimated to the fact that we're going to be looking at clouds in space and we're going to compare them to Earth clouds first. But then there's a section that says schedule missions. And this is where you're going to be scheduling missions to some various objects. And you'll see that there's four nebulae that you need to capture, but you only need to capture one nebula from each of these tables. So we give you a bunch of suggestions that you could capture and use throughout the quest. So, for example, let's go ahead and schedule a mission together to the Helix Nebula. Now, on this table, there contain links. And when we click on one of these links, it'll bring you to a page that looks like this. So we'll be able to choose a date in advance. And then if you keep on scrolling, it'll show you a graph of where this object is going to be in the sky for the Canary Islands. Now, instead of just giving you some missions that you could schedule on, you have to answer a question. The question it says to look at the visibility graph for the Canary Islands and what is the best time range to capture an image of the Helix Nebula? Now, when you're looking at this graph, you can see that the object rises in the sky and it hits a peak in the sky and then it starts to set. Now, in general, you always want to capture images in the telescopes when the object is highest in the sky. And the reason why you want to do that is because the light from the object doesn't have as much atmosphere to get through. When objects are very close to the horizon, the light from that celestial object has more atmosphere to travel through, and it ends up distorting the image a little bit. This actually goes back to the reflection nebulae and the reason why the sky is blue. The atmosphere scatters the light from space, and so we don't get a nice image. So we want to capture an image when the object is the highest in the sky, which looks around 4:30 UTC. So if I scroll down a little bit, I can see that, oh, between 4 and 6 UTC is a possible selection. If I go ahead and click on this, it'll say correct. The maximum altitude is reached within this time range. When I click see available missions, I can see that I'm given two possible missions to go on. And it tells you what telescope these missions are to. The first one is Canary 2 and the other one is Canary 1. When you're capturing the Helix Nebula, I do suggest using Canary 1. Both of these telescopes give very impressive images, but I really like how it looks like in the Canary 1. And all you need to do is hit Schedule Mission and hit Schedule Mission one more time, and boom, you're going on a mission to the Helix Nebula. When this time rolls around, you'll be able to get your Helix Nebula image and use it within the quest. Now, I also want to show that if you scroll past the Canary Islands Observatory, the you can schedule a mission from the Chile Observatory, but you still have to answer this question and analyze this graph and see where the peak of the visibility is for the Helix Nebula to answer the question.
Question. How did it get there? I forgot.
How do you get what?
Here, like the screen is showing.
Well, in the quest, there's a table of possible objects for you to capture. And so you only need to capture one of these objects that are on the table, and all of these are links. So when you click on the Helix Nebula link, it opens up a new tab, and you're right there on this page so that you could schedule a mission.
Oh, thanks.
You're welcome. So once you have your images, you'll scroll down to this data collection spot. And here, this is where you're able to select the images that you want to work with for the quest. So if I were to click on um, all of these, I have an image in, but let me remove my Helix Nebula image from this data collection spot and show you what this looks like. Okay, so if I click Find Image, it's going to look through my photo library and pull out all of the Helix Nebula images, the Dumbbell Nebula, the Ring Nebula, all of the images of the possible um, emission nebulae to use for the quest. And here I can see, oh, here's a really nice Helix Nebula image. I'm going to click on that, and it will see that that Helix Nebula gets put into my data collection spot. And when you go through once you have all of your four nebulae images in these data collection spots, when you're working through the rest of the quest, you'll end up seeing those images throughout the quest. And at the end, you'll be able to use those Helix Nebula image and all of the other images to make your poster. So, do we have any final questions before I release you to hopefully start working on some of these quests? All right. Well, if we don't have any image or any questions, I want to say thank you so much for exploring space with me. I hope you have a wonderful time continuing to explore space with SLOOH. Keep scheduling missions. You can do 5 concurrent missions, so make sure you're always on the schedule getting an image from space.
Thank you,
Thank
John. All right, over to you guys.
Okay, if there are no more questions, we'll now take a short 5 minute break before we come back.
You can do 10 minutes.
Okay, we can do 10 minutes. We'll come back at 2010.
Yeah, thank you again, Dr. John and Anna, for your time. Yeah, I know it's a lot of work behind the presentation. I really appreciate all the time and the hard work. That this information is very helpful to our kids. Thank you.
Of
Glad to hear
course.
it. Thank you so much.
Thank you. Hopefully, we can
Happy to
see you
be
next
part of
time, right?
it. See you tomorrow.
Definitely.
All right. See you.
Bye.
Bye. So all others, Tyler, you just mentioned will be back in 5 minutes, right? Or 10 minutes?
10 minutes.
So we'll resume maybe about 2:10, correct?
Yes.
Okay.
System right now at an average speed, and it moves at an average speed about 48 kilometers per second. The fast speed causes Mercury to have a very short year, with only 87.9 Earth days. So first of all, it's all obviously very close to the sun, so its orbit's going to be smaller, and it's also moves the fastest. So obviously, it's going to have a very short year. A solar day on Mercury lasts only two Mercurian years, or 176 Earth days. Um, and a sidereal day it lasts only 58.6 Earth days. Um, so Mercury has a 3 to 2 spin to orbit resonance. Um, Basically, so every 3 spins it does, or every 3 days, I guess you could say, it orbits twice. So because the orbital speed is so much faster than the rotational speed, something interesting happens during sunrise and sunset on Mercury, which is again what this kind of this whole thing is about. The purpose of this project is to explore, explain, and illustrate this unique phenomenon. This is just a basic overview of Kepler's laws. So Kepler's first law states that planets travel along elliptical orbits with the sun as a focus. Um, yeah, that's pretty basic. Kepler's second law states that a line joining a planet and the sun sweeps out equal areas in equal intervals of time. Therefore, a planet travels fastest at perihelion and slowest at aphelion. So basically, the planet will travel at a speed proportional to kind of where it is, in accordance to the sun. And then the third law states that a planet's sidereal period or year is proportional to the square root of the semi-major axis cubed. And I'll explain what semi-major axis is later. And all 3 of these laws were considered throughout this project. I guess I should probably, yeah. So basically, the semi-major axis is the long diameter, and the semi-minor axis is, or sorry, the semi-major axis is half of the long diameter, and then the semi-minor axis is half of the short diameter of an ellipse. So if you think about an ellipse, right, it's like an oval. You have a long diameter where the 2 points are furthest apart, and then a short diameter where it's, or actually, I think there's a diagram in here. Yeah, so you see we have a long diameter here and then a short diameter here. I don't know how well y'all can see my mouse, but So we'll denote the semi-major axis, which is half the long diameter of an ellipse, as A, the semi-minor axis with B, and then the distance from the center of the ellipse to a focus point as C. So we can describe an ellipse with the equation R1 plus R2 equals A, where R1 and R2 are the distances from both foci to a corresponding point on the curve. So you can see on the diagram here, we have R1, which is, so we have a point here, and then R1 is the distance from the point to this focus, and R2 is the point from the distance to, or the distance from this point to that focus.
And
To
R1
focus
plus
two here.
R2 is R1 plus R2 is constant, I think.
Yes, because it always equals 2A, which is the long diameter of the ellipse. So that's that. And then another familiar formula for the area of an ellipse, or not the area, just the ellipse, is x squared over a squared plus y squared over b squared equals 1. The normal formula would be x minus, let's say x minus h squared over a squared plus y minus q squared over b squared equals 1. But
Why the K square?
huh? Oh, well, it doesn't.
HK.
Yeah, it doesn't really matter what the I don't I don't remember what the specific variables they use for that is, but since we're at the origin, h and k would both be 0, or x is 0 and y 0, as it says here. The ellipse can be expressed in polar coordinates as x equals a times the cosine of a parameter. Does anyone know what that parameter is called? I actually have no idea what this parameter is called.
Theta.
Phi.
Oh,
That's
that is
phi.
not. No, that's not theta.
Theta has a horizontal bar.
Phi. It's phi.
Yeah, it's phi.
Phi?
Yeah.
Phi.
Okay.
It's like pi
So-
but with an H.
5. It's
Oh, hi. Okay. But yeah, as x equals a cosine phi and y equals b sine phi for some parameter phi. Y'all will learn that in school eventually.
Yeah.
Yeah. It's kind of more well, it is trigonometry, so you'll learn that at some point if you haven't already. But so the eccentricity of an ellipse is the ratio C over A, where C, as we discussed earlier, is the distance from the center of the ellipse to a focus point, and where A is the semi-major axis. And the eccentricity is basically like how ovular, I guess, for lack of a better word, how ovular an object is. So like a circle has eccentricity 0 because it's a perfect circle, and then a parabola has eccentricity 1, and then Mercury's orbit has the greatest eccentricity of all planets in our solar system. It has an eccentricity of 0.205. So basically, all that means is that Mercury's orbit is the most. I need to find a better term than ovular. More of an oval than any of the other planets.
elliptical.
Yeah, more elliptical. Yeah, it's just more of an oval than any of the other than the orbits of any of the other planets in our solar system. The area of an ellipse can be expressed as A equals pi AB, where A is the semi-major axis and B is the semi-minor axis. So, in order to find the values of A, B, and C unique to Mercury's orbit, they derived the equations based on the aphelion and perihelion, and we observed that the semi-major axis is described by A. What?
Yeah, what was that?
I don't know. We observed that the semi-major axis, which is, which is A here, is described by A equals aphelion plus perihelion over 2. So here is, hang on, let me see if I can. Okay, so you can see here, this would be the aphelion, which is the furthest point away from the sun, and then here you have the perihelion, which is the closest point from the sun. The model here doesn't really do a great job showing that. Because from the model here, like some of these points, somewhere around here look like they would be closer, but pretty sure that's just the model being slightly inaccurate in that terms. It should be slightly less ovular, I think. How do I erase this? I haven't done this in so long. Here we go. All right. Okay. So that's that. And then we can also see that the distance from the center to a focus is described by C equals A minus the perihelion. So again, we have, oh my gosh, hate this. Okay, so we have C, which is the distance here, is equal to A, which is this, minus the perihelion distance here. And that C is on this, the C is equal here, both here and to the left of that axis there. All right. So, moving on. To find the length of the semi-minor axis, we must use the formula R1 equals R2 or R1 plus R2 equals 2A and set R1 equal to R2. So we see here these two distances are equal because that is because we use the point on the semi-minor axis there. And so then we get R equals A. And then using Pythagorean theorem, we can find that B, which is the semi-minor axis, equals A squared minus C squared. So simple Pythagorean theorem there. And then we can also derive A, B, and C in terms of eccentricity. So since eccentricity is defined as C over A, and C is A squared minus B squared, as we can see here, we can rewrite eccentricity as A squared minus B squared over A and solve for B. So we have B equals A times the square root of 1 minus the eccentricity squared. All right, and then using Kepler's second law, we can derive an equation that represents time in terms of area. And we can use area as a measure of time since they are directly proportional. So basically what they have here, basically the amount of the ellipse here that's covered, so the area of the ellipse that is covered is proportional to the amount of time that the planet has traveled since from aphelion. So a function of position that gives time is demonstrated by the equation A of phi equals 1/2 times 1/2 times in parentheses C times B times the sine of phi plus AB times phi, where phi is our oh wait, no, it's not the angle, or it's just a parameter. To obtain the equation in terms of one Mercury year, we multiply A of phi by 1 over AB pi, which AB pi is the area. So in order to get in order to convert the amount of area into Mercury years, we do that. So our new equation is A of phi equals 1 over 2 AB pi times CB times the sine of phi plus AB times phi. And then now we have a function that gives area that gives time. We need to invert this equation to a function of time that gives position, right? So we want to find the position of the planet at a certain time. So they used a software to compute this for them, and then they created an animation that uses the inverted function to show Mercury orbiting the sun, and demonstrates the increased speed of Mercury at perihelion as well as the decreased speed at aphelion. Vectors are kind of complicated, but so we have the sun is at negative C0. Let me see if I can go find the model. 5. Okay, so we see this distance. If this distance here is C, then the sun would be at negative C here. And then so Mercury's position is at A times the cosine of theta t, B times and then B times sine theta t. Again, that's trig. You'll learn it someday. And then so the vector from Mercury to the sun can be denoted by C minus A times cosine of theta t, and then negative B times the sine of theta t. So basically, it's just taking the sun's position, which is C0 or negative C0, and then where's the other model? Here it is. It's taking the sun's position, which is negative C0, and then subtracting the position of the planet, and that gives us a vector, which yeah, so that gives us a vector of the position of that in relation to the sun. This is yeah, but so basically, suppose this thing is the angle of Mercury's rotation. Since Mercury orbits twice for every 3 rotations, the angle to area ratio would be 2 pi over 2/3, which equals 3 pi. This implies that in t time, Mercury would have rotated 3 pi t plus. Okay, anyone know what this symbol's called?
Gamma.
Which one?
This
Oh.
one's gamma.
Gamma? Oh.
Okay.
And then the subscript, I think it makes a gamma null or something.
It doesn't. Gamma zero. I don't think it really.
Yeah, I think it's
matters,
gamma
but
null.
yeah. But so Mercury would have rotated gamma equals 3 pi t plus gamma 0, where gamma 0 is the initial angle. So hence the vector for Mercury's horizon line. Nope, I moved that. Is the cosine of 3 pi t plus gamma, comma sine of 3 pi t plus gamma. I used a lot of trig in this. This is not very kid friendly. So here we see, yeah. So there's the vector for the horizon line. Here's the vector for Mercury to the sun, and then these are just more arrows showing the vector for the horizon line at different points. So that's not very fun to explain. Yeah, so basically they find the angle between, with this stuff, they find the angle between the horizon line and, wait. Yeah, so basically they find the angle between the horizon line and the sun, or the vectors for the horizon line and the sun. So basically what angle the sun is in relation to the horizon line that you would see if you were standing on Mercury. And so they produce these, oh my gosh. So they produce these graphs here. So basically you'll see negative, in the negative zone would be it's under the horizon, and then in positive it over the horizon for the sine function. So but the interesting is you'll see here, so you start at -1, so it's the sun's like completely not visible, and then you go up, you go up, you go up, and you get to about like 0.42, and the sun comes over the horizon for a bit, and then it goes back down at 0.5, and then it comes back up later at about like 0.57 or 0.58. And so with the cosine function, it's kind of less noticeable with the cosine function, but there is a slight dip around 0.5 as well. So as you can see from these graphs, there's a strange occurrence at t equals 0.5 and 1.5. So also with the sine function you see here, so the sun will briefly go down in between about 1.4 and 1.5, or yeah, it'll briefly go down and then come back up at 1.5, and then it'll go back down around 1.6. Yeah, both these functions dip at these values for t at t equals 0.5 and 1.5. And then so you might be wondering how does this
Basically,
apply?
first it rises, then it dips a little bit, then it continues rising, then it goes down, it rises a bit, and then it continues going down.
Yeah, so basically I don't think this is really necessary either. But basically the unique phenomenon that we have yeah, the unique phenomenon occurs because when Mercury is at perihelion, its orbital speed is so much faster than its rotational speed, which causes, if you were standing on Mercury and you were watching sunrise or something, you could see a double sunrise during a single perihelion passage and a double sunset during the next perihelion passage, which would occur during the same solar day. So, yeah, that basically is what that's basically the presentation. So with all that, you can see that you would perhaps see like two sunrises or two sunsets on Mercury, and that's all because of how much faster Mercury's orbital speed is compared to its rotational speed. All right. Any questions? Here are the acknowledgments and the references. What is going on in the chat?
Oh, we're talking about NWA map scores.
Oh.
Bro, my EOY map score glitched out, so it didn't tell me. It glitched out for the entire school.
My map score was 263.
Sean says he's about to fall asleep.
Why is it so quiet? I don't like this.
Yeah, was my presentation that boring, guys? I'm kidding, it probably was, but
I mean,
You
like,
you said you were teaching about Mercury. Just 1% of that presentation was about Mercury. The other
I didn't say I was. Hey, I
I would
didn't.
probably be more interested if you taught us the 3 more advanced trigonometric functions and gave us a bunch of problems to do.
I didn't say I was going to teach you about Mercury. I said I was going to teach you about sunrise on Mercury, which is literally the title of this presentation. So
And also,
That makes
and also the questions were complicated, so I don't understand because I'm a first grader.
yeah. Eddie, do you want me to teach you trig?
Sure. Bro, I'm actually kind of slow on trig, bro. I forgot what law of cosines was. What was it?
Tyler, can I teach them some trig while I have some extra time?
Yeah, sure, go ahead.
Please. Bro, we have 25 minutes, bro.
Yeah, okay. You forgot law of cosine? That's kind of sad. But let me just briefly show you guys basically what the coordinates came from.
I love Deadpool.
Okay, so let me just briefly explain kind of where the coordinates came from in the presentation.
Like my math teacher is teaching me pre-algebra. He sometimes in break We use Desmos to play with it. So yeah.
We use Desmos for learning
Pre-algebra in 3rd grade? That's crazy. My math teachers are so
Yeah,
BS.
we learned pre-algebra.
We learned pre-algebra.
I also learned AMC8.
I'm in gifted and
Who was
talented.
learning AMC8?
I'm
Who
in
was
gifted
learning?
and talented.
I'm Sabrina's twin.
Rob, you probably got like the award for most comments on everything.
Yeah, definitely.
Yeah.
Oh wait, this is just.
Sibin, I bet you're gonna get like 5 on AMC8.
Look, he's teaching trig. Everyone, he's straying away from what he's supposed to be doing, and he's teaching trig.
Guys, let's take a
Okay,
screenshot
so-
of Rob's screen. It's probably like 20 comments.
No,
Okay,
it's probably
basically-
like 500 comments.
Willie, what?
They say I comment too much on SLOOH.
Yeah.
I don't
on my
know
moon
what it looks
moon
like on there,
observation,
so
on my moon observation, there's 10 comments and 9 of them are his.
what?
No,
On one of the observations, there's 10 comments, and 9 of them were from Araf.
Gosh, dang, what's he saying?
He's just.
He's just saying, cool, nice. Blah, blah, blah.
Yo.
Comment. Like all of
Oh,
them.
okay, that's how you do this. Okay.
Guys,
So-
look at this. Guys, look at this.
You don't want to learn
gravity
trig?
points,
I'll give
nice
you 10
gravity
minutes
points.
and then we'll take a break. And then, actually, how long do you think you want to do this for?
I don't know. I'm just gonna pretty much explain how sine and cosine play into coordinates.
Okay, yeah. How long's that
That's
gonna
about it.
Oh yeah, the unit circle. I think I already learned
Yeah.
this.
And then
Oh my
next,
gosh! Wait, he knows about the unit circle. That's insane.
Bro.
Okay, so if you learned anything about trig before in the unit circle, you'll know that the sine of an angle theta is the so basically if we have a point on this circle, let's just take root 2 over 2. All right, so let's just do that. So you'll know if we want to take the sine of an angle that actually, if we have a coordinate xy, right? For a coordinate xy on the unit circle, the sine of an angle will be the y coordinate over the radius, and then the cosine of that angle will be the x coordinate, right? And so basically where sine and cosine play into coordinates here, if we just simply take with the sine equation, if we simply take r and if we take it and multiply by r on each side, we have r sine theta equals y, and then not yt, gosh dang it. And then with the cosine equation, we have r cosine theta equals x, right? So basically our coordinates are if we have for coordinates x, y, x equals r cosine theta, and then y equals r sine theta, right? So yeah, that's pretty much where these coordinates play, or sine and cosine play into coordinates here in circles and ellipses and all things like that. So yeah, that's about it.
okay, then we'll run a 5-minute break and then we'll go on to Kevin and his presentation about telescopes.
I have very little trig in my presentation, so don't worry. Very little.
Bro. Okay.
Yeah, this presentation had an interesting amount of trig, and I didn't realize it until I already told Tyler I was going to present it. So
just real quick though, now that I'm retired and I'm doing basically astronomy stuff, I probably use trig more than I use even the algebra, and certainly more than calculus when I'm doing tasks around here. I probably use trig probably once every week or two. Maybe algebra once a month. So trig is important to learn ultimately, especially if you're going to do astronomy.
Guys, if you keep on like actually spamming that much, I'm just gonna clear it.
Okay, that's about 5 minutes. Kevin, do you want to go ahead and start your presentation?
Yeah, I can start. So
Okay.
give me a second here.
You want me to go find it or and put
Oh,
it
no,
in?
I don't think you have it. So let me. Oh, I've got it here.
Okay.
Okay, let me share my screen. Okay. All right. There we go. You should see my screen now, hopefully. And everybody see it? Can you see it, Tyler?
Yeah, I can.
All
Yeah.
right, good, good. Okay.
Yeah.
Of course, my name obviously is Kevin Cottle, Coach Kevin for those of you that are part of the JTAS or Teen Task. So that's me. That's my 16-inch Meade LX200 telescope. That's probably one of my, it's about medium of the scopes that I own. We'll get into that a bit. So I'm going to talk about telescopes in general and ultimately end up with what you consider when you're looking for a telescope and some telescopes that are out there and whether they're good or not. So a couple of important points to begin with. In general, and this is not as true as it once was, aperture or how big the mirror or the lens or whatever is generally the most important thing when buying a telescope. The aperture determines how much light it sucks in, and it also determines things like how much power you can use. And for photography later, it determines how long and short your exposures are. But, and this is an important one, this sounds like Captain Obvious, but the best telescope is the one you will use the most. What does that mean? Well, when you look at telescopes, think about how big that telescope is. For instance, I've got a 20-inch telescope that weighs 250 pounds and stands about 6 foot tall and about 3 feet wide. So the question is, how do you move something that big? How are you going to observe it if you've got to move it in and out of your house, for instance?
Yeah.
If it takes three people to move it, you're never going to use it.
That's not.
Yeah, the first time I used it, it took four people to move it. I came up with better ones later. Okay.
To be honest. No, Wendy, I can't log on.
So, so can you move it in and out of the house? And if you're certainly for young people such as yourself, do you need your parents to move it in and out of the house for you? And that's going to limit how much you use it. If you can move it in and out, then you're going to use a lot more than if you have to wait for your parents to come out and help you move it. Where will you use it? How dark is that site? We'll get into that in a minute, and that's a thing called light pollution. How easily can you find objects? If you can't find things very easily, you're going to stop using it. Complexity, how hard is it to set up and use? It takes you an hour to set it up and an hour to take it down. You're not going to use it as much as if it's something simple you can take out, set down, and instantly start using it. And once again, like I said, weight, can you move it in and out? Does it take two or three people? Heavier telescopes get used less. So these are some things to think about when you're looking at telescopes, how much they weigh and how big they are. Okay, I know there's more than three pictures here, but in general, there are three types of telescopes or refractors, which I think was it yesterday or day before they were talking about the telescopes. Refractors use a lens, reflectors use a mirror, and then there are what are called catadioptrics. And let me show one first. So this is the Newtonian reflector. It has a mirror at the back. Can you see my cursor? Hopefully you can.
Yes, we can.
So the Newtonian has a mirror at the back, reflects it to a flat mirror near the front that reflects it out the side of the tube. It's named after Isaac Newton, who's the one that invented this type of telescope. Until then, they would use refractors. Then there's a guy named Cassegrain who made the Cassegrainian focus or Cassegrainian telescope, which uses a curved secondary mirror that sends the light back through a hole in the primary mirror. These are much harder to make. They typically have longer focal lengths and so on. Then you get in what are called the catadioptrics. CAT telescopes. You have the Schmidt-Cassegrain telescope, which is probably the most common of the catted optics, or SCT. You'll hear people say SCT or Schmidt-Cass. These use a thin lens at the front that has a very bizarre curve. And then a secondary mirror, it's Cassegrain, so it comes in, light comes in, bounces off the mirror, hits the secondary and comes out the back. The other one that we're going to talk about is the Maxitov Cassegrain or the MAC. If you hear somebody talk about MAC, they're talking about this kind of telescope. And it's similar to the Schmidt-Cass, except for it has a thicker lens up front. And the secondary mirror in the Schmidt-Cass, the secondary mirror is a real mirror. It's mounted to a hole in this corrector plate, as they call it. On the Mac, it's usually a spot of aluminum that's put on the back of this corrector plate and reflects the light back. So you don't have a second actual mirror. It's just a spot on this corrector plate. So anyway, something to note, like this says, on a cast, typically this secondary mirror will basically magnify how long it is. So this might be say it's 100-inch focal length. This is usually at 4x or so that makes it a 400-inch telescope focal length, which is important. We'll discuss that later. And you'll see that. Okay. Telescope parameters, we talked about aperture. That's just how big the opening is, how big the mirror or the lens is. The objective is either a lens, the refractor, or the mirror in the reflector. Focal length, we're going to be talking a lot about focal length, and that's just how far it takes to focus the image from either the lens or the mirror. EPFL is the eyepiece focal. How big, what's the focal length of the eyepiece itself? And we'll talk about that also in a minute. So aperture, focal length. F ratio is simply the ratio of the focal length divided by the aperture. So let's say this is a 8-inch, let's say that's an 8-inch diameter lens. And the focal length is, say, 400 inches, then that means that this is 40 inches, then that means this is an F5. So it's 400 divided by 8 is, 40 divided by 8, I keep saying 400, is an F5. So we call that F5. And we'll talk about this more in a minute. And the important thing to remember about F ratio, and F ratio is probably one of the more important things to think about, especially for getting a telescope to do photography. An F2, or let's say an F4. An F4 telescope is an F4 telescope is an F4 telescope. No matter what the focal length, no matter how big the aperture is, the object you're imaging is the same brightness in all those telescopes. So if you have a 2-inch F4 telescope that has a lens 2 inches in diameter, and you have a 16-inch telescope that has a mirror 16 inches in diameter, and they're both F2s, the image is the exact same brightness in both of those. Okay. That sounds a little odd. What the difference is, in the 16-inch, it's like 8 to 10 times bigger. So it's more magnified in the other one at the same brightness. So what that means, let's say we're looking at a 2-inch at the Andromeda Galaxy, and it just it'll fit in the eyepiece. Okay, it's that brightness, but in the 16-inch, you're only going to see a small portion of it, but it's just as bright as it was in the smaller telescope. Eyepiece focal, we talked about. Here's one of my math, and this is simple. The magnification, or the power, is the focal length divided by the eyepiece focal length. Generally, eyepiece focal lengths are all in millimeters. So, for instance, a 8-inch telescope is say an F10 is about 2,000 millimeters focal length. The eyepiece at 20 millimeters would make that a 100-pound telescope. Okay, so you change eyepieces, you're going to change focal. Eyepiece focal length, you're going to change powers. Field of view is how big an area of the sky you see through the telescope. Usually given in degrees, but sometimes, especially with cameras, it's given in arc minutes, and we'll talk about that also in a minute. To do that for an eyepiece, you have to know the apparent field of view of the eyepiece. We're not going to talk about that a lot. You can look that up online to figure out how to get a field of view of an eyepiece. And that's how many degrees or how many arc minutes or whichever you can see inside that field of view. Okay, one thing you don't hear talked about a lot is telescope mounts. A telescope mount, I'm telling you right now, is more important almost than the telescope itself. I've seen some telescopes that are pretty good telescopes, but they have a really horrible mount and are almost impossible to use because the mount makes them impossible to use. These are two different mounts. This is an alt-azimuth mount. Okay, it's going to go around pointed straight up. It goes around the horizon, and then this axis goes up and down. So azimuth is around, altitude is going up and down. So that's all it does. Okay. In the last few years, alt-azimuths have kind of taken over. They're really nice. They're simple to use. We'll get into some problems they have in a minute. The good ones are the equatorial mounts. Okay. An equatorial mount, you notice that this axis here is angled, and you point this at the north celestial pole, for instance, the North Star. And what that does is then you have a motor that tracks and it keeps the telescope pointed as the Earth rotates. And it's very simple to keep the Earth's rotation canceled because you only need one motor to do that. On the alt-az, both motors on both axes have to be turning all the time to track the object across the sky. And that causes some problems. Somewhere here, I've got a thing that says you got to be real careful about choosing autonomous things. There's things that are called hobby killers, and we'll talk to that in a minute. Now, the other thing you don't see a lot, but when you really start looking for a telescope, things that are important are something called an airy disk. Don't worry too much about that. Basically, the center, the actually edge of the objective, of the mirror or the lens, causes diffraction. It bends the light rays a little bit, and you don't get one dot for a star. What you get is something like this. You get a bright central region, and you get a bunch of rings like that. Okay, and the airy disk is how big that central portion is. That's important. The airy disk is important if you're trying to look at really close double stars. That becomes an important criteria. None of you are probably going to do that right now, so some. A bigger one is something called chromatic aberration. You'll notice that the lens here of a refractor looks a little bit like a prism, and it acts like a prism, and it disperses the light into its colors. So that when you look at this with an eyepiece, you see, say, the edge of the moon, and we'll look at this in a minute, and you'll see color fringes around it. And that's really bad. It's really, destroys your image and makes it hard to see. The other one is coma. All scopes have coma to some extent, and that is where in the center you have a nice round star. Off to the edge, they start looking like comets. Hence the name coma. All scopes have it. It's worse typically with short focus, low F ratio telescopes, and it can be a little hard to call. Diffraction, just caused by physics. I mentioned the diffraction caused by the edges of the lens or the mirror. Anything you put in the optical path, like if you see some telescopes, they have little metal pieces that hold the
mirror.
The mirror, yeah, the secondary mirror, and that causes diffraction spikes like that. Most scopes you run into now that they don't have that as much, but if you get like a Newtonian, it typically will have this 4 vein, and you'll see a diffraction spikes like that. Anything like that kind of messes up the image slightly. Okay, now comes something that you'll need to be a little bit aware of, And that's something called magnitude and surface brightness. Magnitude is something astronomers use to measure how bright an object is. The bigger the number, the dimmer the star, or dimmer the object. So magnitude 0 is about the brightest stars. Magnitude 6 is the dimmest star you can see in a very dark night with your unaided eye, roughly. This is how they set this. So they said the brightest star I see is going to be 0. The dimmest one I see is going to be 6. Long ago, they decided on that. And then the whole thing is based on that. For each magnitude difference, it's about 2.6, 2.5 times bright or dimmer. So a magnitude 1 is 2.5 times dimmer than a magnitude 0. Magnitude 2 is 2.5 times dimmer than magnitude 1, and so on. I'll show you some of these here in a minute. The larger the magnitude, okay, it's kind of backwards. The larger the magnitude, the dimmer the object. Sun is minus 27 almost. Moon is like minus 12.6. Okay, that means they're extremely bright. But the problem is magnitude is not a good indicator of what I call extended objects, galaxies, nebula, and so on. For that, you'll want surface brightness. And surface brightness can be hard to come by. Most places don't really publish that, and I don't know why. When you're trying to pick an object to look at in the night sky, that's what I use to determine how good it's going to be. So, for instance, the Andromeda Galaxy is 3 times the size of the Moon, so magnitude 3.44, but in reality, its surface brightness is closer to 4 to 5. Triangulum Galaxy is even worse. It's double the size of the Moon. Its magnitude is 5.72, which sounds like you could barely see it in the night sky, but you can't, because the surface brightness is closer to 13. That means it's fairly dim. So if you look at though online, it'll go, oh, that's magnitude 5.72, and you go, oh, I should be able to see that. And in fact, it's a lot harder to see because the surface brightness is so low. So here's once again magnitude over here, starting with magnitude 1 to magnitude 15, and how much dimmer it is than a magnitude 0. So a magnitude 1 is 2.5 times difference. Go down here to magnitude 6, and that's 244 times dimmer than a magnitude 0. Anybody in here know binary? Anybody know what the closest binary equivalent? How many bits is 244 roughly? Anybody knows? So basically, that's 8 bits of resolution on the camera, for instance. Okay, 8 bits of resolution. So our eyes and brain is about an 8-bit wide system. That's how many bits are in the word or the information that you get out of the camera. You see that between a 0 and a 15th magnitude is almost 15th magnitude is almost 1,000,000 times dimmer than a 0 magnitude. So these things are getting really dim. Over here, this is one I pulled out of a program that I wrote that I use for different things. So Rigel is a star. You'll see that its magnitude and surface brightness are the same. The Orion Nebula, you'll see it shows a magnitude 5. In reality, its surface brightness varies from about 5 down to 12. Venus is it's slightly extended, so it's about a -2. That's a star. Let me find Eskimo Nebula. It says it's an 8.6. It's really more of a 12 because of the surface brightness and so on. So you see that things are a lot dimmer in reality because they're spread out over wider. Minimax, this is arc minutes, how big the minimum size and the maximum size of these things are. Okay, so real quick, I've talked about that. Somebody talked about that the other day, and we talked about this a little bit. So if this is a degree here from these 2 white lines, that's 1 degree, then there are 60 arc minutes in a degree. Okay, so this is the size of an arc minute if this is a degree. Each degree is broken into 60 arc seconds. Okay, so this is 60 arc seconds. It's all crammed. If I would have put it in this space, it had just been a green blob. See, that's why I expanded it out. So between this side, the left side and the right side, there are 3,600 arc seconds. Okay, so an arcsecond is a pretty small measurement. But this is what astronomers use, arc minutes, arc seconds. And when you look at I think I had so Venus here is 0.2 arc minutes. So that means it's really about 12 arc seconds. Okay, so it's very small. So you can measure degrees with your hand, and it's just very useful. Doesn't matter how big you are, because your hand size compared to your arm length varies about the same as anybody. So my hand at my fist at when I'm got it at arm length. This is all at arm length. My fist is 10 degrees. So if you put your fist out and look at it, that's about 10 degrees of the sky. You know, your little finger is 1 degree. So hold up your little finger. See how big that is? Now imagine imagine 3,600 pieces in that. That's arc seconds. So imagine 1/3600th of the width of your finger there, and that's 1 arc second. It's extremely, extremely small. So, but this is a good way to figure out how big something is in the night sky. I use this a lot. And for instance, you get you a telescope that needs to see Polaris to do an alignment. You need to see the North Star. And you live in the city, and let's say your house faces south, and you're going to use it on your front driveway, and you know that Polaris is 34 degrees above the horizon. Okay. So what you need to do is figure out where you can put your telescope where you can see Polaris. So you go out on your driveway and you hold your hand out and you do one fist, then go up, do another one, and up another, that's 30. And then once again, about 3 fingers, and that's 34, 33, 34. So I use that a lot to figure out, can I see an object from where my telescope is going to be? And I'll sit around my driveway and go, okay, here's a space where I can see not only Polaris, but also the objects that I want to observe. Aha, that's good. So I use this all the time when I'm setting up my telescope, trying to make sure that because the last thing you want to do is get it all set up and then find out, oh, I can't see Polaris. Oh, I can't see the object I'm looking for, and I got to pick the scope out and start. So this is a very useful thing to do. Okay, size of different objects. This is to scale. So this is Mercury here. This little tiny dot. Actually, it's even smaller than that. So on this scale, this is Mercury, size of Mercury. This is Venus. The little dot on top is how small it is when it's on the other side of the sun. And the big dot is actually, it should be a crescent. That's how big it is when it's on this side of the sun, same side as we are. Mars is even worse. It's a tiny, tiny little dot when it's on the other side of the sun. When it's at its closest, it's about this size. Jupiter varies some, not as much, and so does Saturn. Okay, but this is about the relative sizes of these objects compared to the moon, which is okay. So this is 1 degree. So the moon's about a little over half a degree. Andromeda is actually about 1.5 to 2 degrees in this long dimension. M81 is pretty good size. Ring nebulas, once again, getting down about the size of a planet. And you'll notice that, okay, it looks a little bit bigger than Jupiter. And the ring nebula and other planetaries, he talked about that today. That's the reason they call them planetaries, is because when they first started seeing these, they look like planets. And at first they thought they had discovered a planet, and they realized, no, it's not moving. It's something. And so they called it planetary nebulas because in the early telescopes, they look like little planets. So planetary nebulas are very small. M81. This background picture, by the way, is the North American Nebula. It's very, very big. Okay, it's like 2 by 3 degrees. It's huge. So those are the sorts of things you want to think about when you start looking for a telescope. You want to find a telescope. Okay, what do I want to look at, and what am I going to do, and what telescope is best going to do that? I'm going to talk a little bit right now about the electronic telescopes, and I'll talk about that more in a minute. But the newer electronic telescopes, the C-Star S50 and the Dwarf 3 and the S30, the red is how big a field of view it has. Okay, its camera. The Dwarf especially has two different ones. I'm using the wide angle. And what you see is, okay, the Dwarf is good for the moon, Andromeda, and maybe one. Ring Nebula is okay. Certainly good for the North American Nebula. The C-Star is pretty good for all that. These things have a thing called mosaic where they can move the picture around and build a big picture. So they can all do big scale stuff like the North American. What they don't do good on, the dwarfs, the C-Stars, and so on, are the planets. The planets look teeny tiny. And I think Tyler has a S50. Tyler, isn't that right? You can't really see the planets very well. Is that right?
Yeah, you can't really see the planets really well, but you can see the moon well.
You can see the moon. The moon's good, and they come with solar filters, and you can see the sun, which is the same size as the moon, basically. So you can see the sun, the moon, and really all these other stuff. You just can't see the planets for it. Okay, this is some C-Star 50. This is wrong. This is not the right. Ignore these. This outside green ring is how big, and we'll look at a telescope in a minute called the Library Telescope. It's a 114 millimeter scope at 25 eyepiece of 25 millimeters. That's how big it sees. So it sees quite a bit. This is an 8-inch telescope with a 25 millimeter telescope, the smaller circle. So it can see now these things start looking a little better in that. And you can add and replace the eyepieces and look at different sizes. So with the telescope, the eyepiece will change and you can see these things quite well. And we'll talk about that too. Okay, I'm sorry. This is the Library Telescope with the maximum power of the big one and the minimum or the maximum power of the little circle, which is 8 millimeters and 25 millimeters for the outside. This is the 8-inch with this is an 8-inch with the low power with the big circle and the high power with the little circle. You can see now when you start looking at Jupiter and Saturn and the moon and stuff like that with high power, you can see craters and you can see the stuff on Jupiter and so on. So by changing your eyepieces out, you can see different objects at different scales. Different telescopes, different views. Once again, we talked about the F ratio. These are both F4 telescopes. This is a 4.5-inch scope. That's the Library Telescope we'll talk about in a minute. You can see, okay, it's about this size, and let's say it's that bright. It's not in the Library Telescope. It's the same brightness in the 8-inch telescope view, except it's quite a bit bigger. It's about twice the size in the 8-inch, but it's the same brightness. So, and F4 is an F4. It's just that there you get to see more of it, and it's a lot easier to see. That's what the telescope size does for you. Once again, different scopes, different views. This is a planet. So this is Jupiter. This is all of 8 millimeter. And 8 millimeters is what I call a high power. Once again, 2 F4s. So we got a 4.5-inch F4. That's what it would look like in the Library Telescope. You can barely see the bands on it. On an 8-inch, you start getting a lot better. The 8-inch F4 with an 8 millimeter at 100 power, you start seeing the bands pretty well. An 8-inch F10, which is like a Celestron C8, you're going to see the bands quite well because this F10 ratio is a lot longer focal length. Focal length of this one is 320 millimeters. The focal length, F4 is about 800 millimeters. This one, F10 is 2000 millimeters, so that eyepiece now gives you a lot better view. The 16-inch, my 16-inch F10 out here, 8 millimeter eyepiece gives you a very big field of view. And we'll talk about some problems here in a minute. But in general, you can add eyepieces, change eyepieces, and find the view that matches. Okay, now we get into some problems. The biggest problem you're going to see, well, there's two big problems. One of the big problems, especially in the city, is seeing. And that is the distortion of particularly stars and planets and the moon, sun, with atmospheric turbulence. That's the air moving around. And when you live in a city, the ground heats up during the day, and then at night, as it cools off, all that heat rises and stirs up the atmosphere, and you're trying to look through all that jumble. It's like looking from the bottom of a swimming pool and somebody swimming in it and messing all around. It really messes up your seeing. And that's what astronomers cause it. And telescopes are going to magnify that effect of seeing. And if you just look with your unaided eye, if you look out at a night sky and you see stars twinkling, that means there's bad seeing because stars will twinkle. Planets don't twinkle. If you see something that's everything else is twinkling, but something bright isn't, that's a planet. They can also be caused by weather. If you're in an area where there's hills or mountains or large buildings and the wind goes around there, it's going to cause turbulence. Once I already talked about heat rising from buildings and pavement. Best thing is given in arc seconds. It is typically half to three-quarters of an arc second. See, you get that on top of a mountain with a very clear night, very stable night. You're never going to get that in Dallas. Seeing around Dallas is typically 2 to 4 arc seconds. Now, if a planet, we were talking about a minute ago, Jupiter and Venus are around, say, 20 arc seconds or 30. 2 to 4 arc seconds is going to mess up pretty bad. You're it's going to blur out all the little features, especially on Jupiter. Every once in a while, and this is where visual is a lot better in some ways, looking at it, every once in a while it clears up just enough for you to see things real stable, and your brain will kind of remember points. Once again, the sun, moon, and planets are the main thing that are affected by seeing. The stars are as well, but typically you don't notice as much. Something odd is smaller telescopes will often outperform big telescopes in this effect. And that's because it's looking through less of the atmosphere. A very small telescope, say a 3-inch telescope, is only looking through a pipe about 3 inches in diameter. And so it's only seeing a small amount of this turbulence, whereas a big scope on a 16, when it looks through there, is looking through a giant 16-inch swath of sky diameter, and it really sees everything in there. So what that can mean is a smaller telescope can often, especially on planets, can see more detail than a large telescope. So keep that in mind. If you want to do planets, don't go out and get a 16-inch telescope. A 5 to 8-inch telescopes will usually do much better. One night I had my 8-inch out at a star party. There was a guy there with a 3-inch telescope. The seeing was bad, and his 3-inch telescope was showing far more detail on Jupiter than anybody else. And okay, let's see. Okay, so somebody had a picture of that. Oh, the North American Nebula. They had I'm not watching the thing, so they had a picture of the North American Nebula. Okay, so now the other thing in the city that you're going to notice is light pollution. So this is what the sky looks like from, say, used to be where I live in Princeton. This used to be what I saw when I looked out my backyard. Okay, I could see all the stars. I could see the Milky Way. Things were nice. And I could see most of the stars. And I could find things very easily with my telescope. It didn't have a computer on it, but I could see things easily because I knew where they were. And I could see the stars that guided me there and see the constellations and so on. But this is what you're going to see if you live in a big city like Plano or Dallas or wherever you live. If you're living in a city, all of a sudden you're not going to see. You're going to see. Let's go back. You're going to see Altair, Vega, and Saturn, but hardly any other stars. And you're certainly not going to see the Milky Way. Okay, because the light from all the street lights and everything that's blasting up into the sky, and it just wipes everything out. And this is called light pollution. And so that's why it's hard to observe from inside a city. it's a lot easier to do it out at a dark side. Our club, if you're part of the J test or Teen test or part of an astronomy club, most of them have a dark side. We have a dark side up in Oklahoma that looks even better than that. It's very dark. You can see the Milky Way. You can see all the stars. It's very nice. It's an hour and a half to 2 hours to drive from Dallas up there, but it's very nice. So, um, yeah. So, okay. Looking on some of the things. So let me stop here for a second. Is there any questions? I see a lot of stuff in the chat I haven't been able to watch. Question?
I have a question.
Yeah.
What in light pollution? I'm pretty sure light pollution is like based on like Bortle levels, but like, can you explain them to me? I don't know
Okay.
much
Yeah.
about Bortle levels.
So there is a scale astronomers use called the Bortle scale. And the higher the number on the Bortle scale, the darker. Find that right? No, the lower the number, the darker. So our dark side is like a Bortle 2 to 3. If you go out to the Texas Star Party, it's around the Bortle 2. If you're out in the middle of the desert in a good night, you might get Bortle 1. Around Dallas, you're going to be looking at Dallas at Bortle 7 or 8. So it's just a measure of how bright the sky is. There's a new scale people use called the Sky Quality Meter. You can go out SQM. You can go out and buy an SQM, and it goes like I think 0 to like 30. Once again, the lower the number, the better. But you can buy these little meters, and in fact, I think you can actually get a app for your phone that will tell you the SQM values, and that's just a measurement of how bright the sky is. But like I said, you Bortle and somewhere I don't have it on here, but if you start looking at Bortle scales, somewhere I saw something. I think Bortle 5 and below or 4 and below, you can see the Milky Way. You get up above Bortle 5, and you lose the Milky Way. By Bortle 6 or 7, you lose most of the dim stars, and by Bortle 8 or 9, you can barely see the bright stars and the bright planets. Did that answer it? Okay, awesome. Yeah, that's a really
Yeah,
bad.
it did.
Oh, here's the SQM. Okay. Okay, so you can buy these sky quality meters, or like I said, okay, this one's showing 21 to 16. So this is backwards. 21's better. The higher the number on an SQM, the darker the lower it is, the dimmer, or the more light pollution. This is the light pollution map. Okay, you can actually go out and look for light pollution map on Google, and you can find these maps to show you how bad light pollution is in an area. And you can use this to decide where you're going to observe. See where that arrow is pointing? That's where I live. It's actually worse than this now. You know, I'm actually in the white now because they put houses all around. So that's where I live. This one right here is our dark side up here in Oklahoma. Okay, you can see it's quite a bit darker. So it's worth this. And you see that you have to drive an hour and a half, 2 hours out of Dallas before you can get to a dark area. And it's a very nice site. It has a bunkhouse. You can stay overnight. It's air conditioned. It's got electricity and a bunch of pads. You can take your telescope up there. It has telescopes up there you can take out and use. It's a really nice setup. This is where I lived at in Oklahoma when I was a kid. And when I lived there, it was much better. I could see the Milky Way from more. So back then, it would have been more of an SQM 20 or a Bortle, probably about 5. And now it's Bortle 8 or 9. And part of that is because more and more lights have been added. But the biggest problems happened in the last 10 years when cities have replaced the old style street lights with the LED street lights. And the LED street lights they made as bright as they could make them because they're cheap to use and they just make the night sky just like day. It's really, really bad. and it's really made a lot of dark places. But go out there if you want to and look for this slide. I'll try to send a link to Todd. He can put out to everybody how to find this map so you can see where you live. And this actually goes all over the world. It's not just the U.S. Okay, now let's get into telescopes. Now that I've gone through all this stuff. Yeah, somebody said they have a friend in Salina. Salina's probably not too bad.
Yeah, I live in Salina.
You live in Salina? Okay, how is it? How bad's the sky?
It's decent. I can't really say much about it, but you could see the Pleiades with your own eyes, and it's not that bad.
Yeah.
You can
But
see
it's probably getting that way because
cluster.
more people are moving there. So
Yeah, it's good. It went from like 20,000 to like 60,000 in like 4 years.
yeah. When I moved out here to Princeton, it was 3,500 population. It's now almost 40,000. So and they're around my backyard now. My property line is now the city limits, and there's houses all over. So, all right. So what scope should we get? I'm going to talk about. There's a special kind of mount called a Dobsonian mount that I'll be talking and discussing here as we go. It's an alt-azimuth mount. You remember those mounts I showed? It's one that goes around the horizon and up and down. So this is Dobson here. This is the guy that kind of invented this mount. It's very simple. He made it out of plywood, and a lot of them are made out of plywood. And it revolutionized astronomy. Before John Dobson, a 12-inch telescope was a huge telescope. If you owned a 12-inch telescope as an amateur, that was pretty incredible. Now with John Dobson and his Dobsonian telescope mounts, 16, 20-inch scopes are common. And people have 25 and 30-inch telescopes. These things are monsters. You've got to have a 20-foot ladder to climb up and look through the eyepiece. So he revolutionized. Great guy. Unfortunately, died several years ago. When I was your age, I used to stay up. If you ever watched the Tonight Show on NBC, back then it was put on by John Carson. He hosted it, and he was an amateur astronomer. And he would have John Dobson and people like that, other astronomers, on really late at night, and I'd stay up and watch them talk. Okay, so this is one of my 20-inch Dobson telescopes. This is one I built, 40 years ago now. And this is my latest one. This is a motorized 20-inch, and also on a Dobson mount, but it's much smaller. Okay. Yes, somebody asked, is this the library telescope? Yes. This right here, this Aptura, is the library telescope. So I've got one actually sitting behind me here in the room. Team Task owns 2 of these, oddly enough, and you can check those out. And we've got the Little Elm Library north of Dallas also is getting these, and this is for libraries to take and check out. And we'll talk about this in a minute. It's really a good little scope. I played with it. It's a lot of fun. Very simple to use. Okay, real quick, I'm going to pass this real quickly. You can get these very simple sky tracking mounts. This is really for you to put a camera or a tiny telescope on and use it to look. They're really good if you wanted to take those big the Milky Way panoramas and star trails and stuff like that. These are good for that. Okay. Real quick, mention hobby killers, what you don't want. Okay. And real quick, rule of thumb, cheap telescopes aren't good. Good telescopes are not cheap. Okay, that's an important thing to remember. Don't forget that. If you see a cheap telescope like at Christmas, you'll see these things pop up at Walmart and Costco and places like that. And they're cheap, crappy little telescopes, and they're really bad. One way to tell is you see these little bitty finder scopes, actually little telescopes, finder scopes, these things are worthless. And if you see a telescope with a finder scope like that on it, it's bad. And most of the problem isn't the scope itself, Usually it's the mount is so bad you can't aim it. You really almost can't aim it. I actually have one of these Celestron 70s. A friend gave it to me, and I actually used the telescope for a long time on my 20-inch. It was on this scope right here as a finder scope, and it made a great finder scope. The optics in it weren't that bad, and but on this tripod, it was horrible. You couldn't use it. Same thing with this one. We use these. We use these in our NASA camps to talk about telescopes, the different kinds. This is a Newtonian reflector, and this is, of course, a refractor. If you do have one of those, one way to make it better is using don't use this cruddy little finder scope. Get you what's called a red dot finder base. Now, if you have one like this or this, they make a little red dot finder that's meant to, has these two little holes that'll fit on the screws. You see these screws here on this one, and you can replace it, and that helps out a lot. The red dot looks, you look through it and it projects a dot on the sky, and you can use that to aim the telescope, and it's so much better than these things. I use red dot finders once again. You see one right there. There's a red dot finder on my 20-inch. I use a red dot on my 20. This is a red dot on the Aptura. This one right here is what's called a Telrad. It was one of the early red dot finders. You don't see those much anymore. They were great big. These are very small. Okay, real quick, I'm going to talk binoculars. What's a good first telescope? Binoculars, oddly enough. 10 by 50s are kind of standard. You can get them for around $100 on Amazon. I've got a pair of 10 by 50s sitting behind me here in my office. I've had almost 50 years, and I still use it. You buy a good pair of 10 by 50s, and you'll have it your rest of your life, like I have. Hopefully today and the rest of my life, and hopefully it lasts me another 20 years, but we'll see. Another interesting pair are these right here. These are, okay, so the first number, by the way, is the power. So this is 2 power by 54 millimeters is how big the lenses are. So the lenses on this are 50, the power is 10. This is 54, and the power is 2. And that sounds kind of weird. What good is 2 power? But I tell you, you go out to the dark side and you look through these binoculars, and it's like having owl eyes. It's like having the eyes of an owl. Suddenly you see all these stars appear because you just see the whole sky, but now you just see hundreds and thousands of stars. It just makes the stars more visible. And they're really nice to have. Unfortunately, telescope.com doesn't exist anymore. But you can find, because Orion doesn't exist anymore, but you can find there's Vixen and others have these really wide angle binoculars. And they're an interesting pair to have. I get a 10 by 50 before I got those, but I've got both, and they're both very useful. And this gives you an idea on the 10 by 50. You know, you can see the moon is going to be small. Jupiter is going to be a tiny dot, but you can see the moons of Jupiter with the 10 by 50. And that's almost what you're looking at is what Galileo saw with his telescope. You can see things like the Andromeda Galaxy, but little bitty stars and close stars aren't going to be very good to see. But star clusters, the Pleiades, other star clusters, globular clusters to a certain extent, but other things are going to be great. And so I often will take my 10 by 50s with me when I observe, just to get a quick snapshot of what's up in the sky and see wide angle things like the Pleiades. Okay. Something new that's come out, and I talked about it a minute ago, and that's electronic telescopes. The Dwarf 3, the Sea Star has a 50 and a 30. That's how big the lens is in front. And the Celestron Origin. But the first two, the dwarfs, and there's a Dwarf Mini now, and the ZWOs. They're a refractor. And they have a camera. There's no eyepiece. There's just a camera. The nice thing about these, you can take them outside. You set them down. You turn them on. You tell them what to do. They find where they are in the sky, and then you just tell them, "I want to take a picture of Andromeda. Pick your star cluster or whatever, the moon or whatever. It'll zoom. It'll slew over there, and take a picture." So They're really handy. The other thing good about them is you can use them pretty well in the city. You can actually get reasonable images of galaxies and star clusters and nebula from inside your house, not inside the house, from your front yard or backyard. So they're really, really nice. And they're cheap relatively. I mean, they're $550, but compared with alternatives, they're really nice. The only thing is you can't change the power much on them. The Dwarf has 2 powers on it. And they're really bad for the planets. I shouldn't say bad, but they're just not very good. But other than that, they're a nice, handy telescope to have. If you're really into astrophotography, you can look at the Celestron Origin. It's $4,000. It has a 6-inch telescope, one of the Celestron 6-inch rososcopes, really nice. A lot of people I've seen have these. They make excellent, fantastic astrophotos. This would be the professional version of these two, but for just starting out, these two make a good scope because you can use it. Problem is, you're not learning how to point the telescope. You're not learning where things are in the sky, and so you've got to kind of But ultimately, I would say this is going to be what most people are going to get because, like I said earlier, you're going to use this more than anything else. I know Tyler has a couple of other telescopes, and he's got an S50, and I think he used the S50 more than anything. Is that right?
Yeah, it's the easiest one for me to use. I don't have to do some crazy setup.
All right. So it's once again, if it's easy to use, you're going to use it a lot. If it's not easy to use, you're not going to use it. So that's why I put this first. That's a good scope. I can't in a way I'm a little hesitant because I don't like them because you're not looking through them and you're not you're not learning the sky as much. But there's still get you in there and now it's just like taking pictures with the SLOOH telescopes. You tell it where you want to do, and it goes out and finds it, and it takes the picture. I'm going to go from that. I'm going to skip several here. I'll go back and pick up some other telescopes. And that's the Maxitoff Cassegrain telescopes. I showed that earlier. That's the one with the curve that has, you see, these have a aluminized spot on the center, not an actual secondary mirror. And the reason I'm showing this with this, they make a good complement to that. So if you get your electronic telescopes, next one I would get is like about a 5-inch or 127 millimeter Mac. And the reason is these things are pretty good on planets and fine detail on the moon. And they're small, so they have a pretty good, aren't as affected by the seeing as other telescopes. The other thing is they have long focal lengths. You see the F ratio is really big. F ratio on these things tend to be about F4, F5. Here, these things are like 12 to 15. So you put a small, like a 25 millimeter eyepiece, which is kind of a low power eyepiece, and it's a high power piece because they have such a long focal length. So these are really good on planets. I've got a 7-inch Mac. We've got a 7-inch Mac that belongs to the club that you can check out if I've got to put it on a mount, but those things are planet killers. I mean, they are excellent on planets. The 7's really good. The 5s are almost as good, and probably on days of bad seeing are even better than the 7s. So these two in combination make a great combo of scopes that you can use, because then you've got the planets, the moon, and then you've got the electronic telescope for everything else. Refracting telescopes. These Celestron Star Sense scopes, and there's several of them, aren't too bad. This is a 102 millimeter, so about a 3.5-inch, 4-inch, about a 4-inch telescope. Not bad. Once again, uses a lens. The problem with this one is you're going to have some color diffraction. So you're going to see color fringes around things like the moon. And this gives you an idea about what that telescope, so this is a galaxy, star cluster, that's moon at high power, moon at low power. And so it's not a bad scope to have. These use your phone. You put your phone on there, and it helps you aim the telescope. Now, when we're talking about refractors, there's several different kinds. You don't see single lenses, thank goodness, anymore. Occasionally, back years ago, there are some really unscrupulous dealers that use single lenses, and they were horrible. Couldn't see anything because all you saw was color bands. Other long ago, they learned that if you take one type of glass and use a different type of glass and stuck them together, they would really help with the color. You could get them to focus much closer together. And then what they did, they made a very long focus. So when you make it long focus, so you make the F ratio F15 or so, then the color separation isn't as bad. So that's why you saw, if you remember a couple of days ago when she showed the 30-inch telescope or 36 telescope up at Yerkes, it was extremely long. Remember that giant telescope? It was extremely long because it has a doublet, and if it's not that long, it was really bad. Now, using modern glasses, they have all these different kinds of glasses, and now you have apochromatic or ED. You'll see it, ED or epichromatic, and there are epichromatic ED or ED doublets, which is 2 lenses, and most of them, the really good ones, are 3 lenses. Problem is, this glass is expensive. The very fancy glass they used to make this.
These ones, you need a whole lot of lenses.
Yes, it's heavier too.
Like 3 lenses, that's like pretty hard to make, like pretty expensive compared to 1 lens.
Exactly. Yeah. So EDs. So let's say an 80 millimeter achromatic or doublet. Okay, you can probably get one of those 80 millimeters for around $250 or $300. The ED is going to be like $800 to $1,200. Okay, where you use this typically, the ED is when you're doing astrophotography. When you really get into it and want to really do good astrophotography, you're going to get it like an 80 millimeter ED scope or apochromatic triplet. So this is the difference. This is a regular achromatic. This is a doublet. This is an ED-LD. This is where you have a special glass, and it's better. Doesn't look that way, but you have a little better on color. And if you do a full apochromatic ED triplet, then you don't see really any color. But each one of these costs more. So there's your example. A cheap ED is the SV503 80 millimeter from SV Bonding. Very good company. I've worked with them, and it's about $430. Explorer Scientific is about $900. It's a triplet. This is a doublet. The SV Bonding. The Explorer Scientific is a triplet. This is the Starfield Optics ED80 Gear 80 is around a $1,400 telescope. I have one of these. I had one of these Explorer Scientifics. I sold it and I got this. I did not buy this. I got that as a door prize at a conference I went to out in California. And so it's a really super nice scope. Couple of people have used it in the club to do research with. It's a really nice 80, but you can see it costs a lot. Okay, talked about the Newtonian reflector. I have the little celestial star sense here. It's similar to the Aptura library telescope. Library telescope doesn't have a camera mount to mount your phone, but it's about $450 for the Aptura. And these are pretty good. They don't have color. Fraction is fair because they have the spider in the front. But you can see pretty good views of the moon. The planets and are okay, not great, and the things like the Andromeda Galaxy, you can see those. Dobs, I mentioned the big Dobs. An 8-inch runs around 850. One with Go 2 motors on it with SLOOH itself is $1,600. And I'm going to post this. I'm going to post this so you guys can look at this. But an 8-inch, once again, you're going to see the Andromeda Galaxy is going to be much brighter. The moon's going to be much closer. Planets are going to be much better. Star clusters will be better. So it's really good for everything. You got a bunch of these Star Sense Explorers. I'm not going to go through every one, but the 5-inch one we have here is that people can check out, 130. And you can buy these up to a 12-inch stop. or $1,600. Once again, you use your smartphone to aim, and they work okay in the city. You can actually. Then you have things like the Nexstar 5s, 6s, 8s. That's this kind here. They're aldazimuth, but they're single armed. They're okay, but once again, the different sizes, you can see a lot more things like that. Now, if you really want to pay some money, the CPC series is really nice. The problem with the CPC is these are heavy. The 8-inch over here probably weighs in at 25 pounds. The 11-inch goes up to like almost 60 pounds for the telescope. It's pretty heavy. I've used all those. They're really good. They're good scopes. They're really easy to use. They're fun to use, but they're expensive. CAS has a loaner scope, an 8-inch. We've got a couple of loaner scopes that are 8 inches that are part of the junior clubs. So we have the 8-inch LX9 as well. The Schmidt Cassegrain telescopes are really nice. The Celestron 6, 8, and 9 1/4. You can see the prices there. These are excellent scopes. Hansen has one of these. He uses for astrophotography. He's 6-inch. They're really good scopes, all around scopes. Certainly on planets and things like that, they're great. Okay, so really any questions? I kind of ran through those real quick. Okay, what is your opinion on the go-to telescopes like the Nexstar 8 SE? Let's go back. So the Nexstar 8 SE is okay. We've got a 5 SE here that the club owns that you can check out. The 8-inch is nice. It takes a bit of getting used to setting it up. You have to aim it at like 3 different stars. So it's okay, but you have to have a little bit of patience to learn it. Somebody asked, do you know GPR? What's GPR? I don't know. Is that a company? Sabrina, is it? Sabrina asked that question.
Ground planetary radar.
I'm sorry, it's what? Ground penetrating radar. Yeah, I know about it, but that's kind of a little out of our scope.
I know.
Yeah. The Evolution series, let's see, is that Explore Scientific, I believe? No, okay. Oh, Celestron. Evolution. Is that the no, that's no, that's the Origin. I am not very familiar with the Evolution, I'll be frank. Okay. Yeah, okay. Now I know what you're talking about. Yes. They're okay. They would be once again halfway between the Nexstar and the CPC. You're right. They're a little better scope, a little better map. So they're a good scope to have. The Nexstar are okay starting out. However, once again, expect to take it's a learning curve. You'll have to take some time. And let's see now. So which scope should you get? Well, looking at all that information, my answer is all of them. You need all of them. So these are all my scopes. And you see, when you get as old as I am, you collect a lot of better scopes. So these are binoculars. This is my 16-inch with my 5-inch ED scope on it. This is my Questar 7. Questar unfortunately just went out of business. These are very expensive telescopes. I didn't pay for this one. 20-inch, 20-inch. This is my C11 right here. I got to do asteroid work. That's my latest one. That's a really good little scope. Love that scope. So. Oh, how much did all this cost in total? Oh my gosh. I don't think I want to know. A lot. I would guess if you look at every scope I've owned and all that. Oh gosh, it's probably in the 40,000 range. But we don't talk about that, especially once you're married. You don't talk about it. Number of telescope. I tried counting them once. I think it's around 20 now, counting all the little ones. These are the ones I use the most. This is the little Gear 80 scope I was talking about. These are the little C90s, Celestron 90 millimeters. I bought this oh gosh, this was over 40 years ago. I bought that to observe an occultation of Saturn where it went in front of a star and you could see the star. And I was going on vacation, so I couldn't take the big scope. And I bought that to stick in the luggage and take and watch the occultation once I got there. But it's been an interesting little scope. Okay, so that's all I've got. If there are any other questions, and I'll give this to Tyler. Oh, George, did you have a question?
Yes, I do. I have a Newtonian telescope, but I never really understood the whole using the stars to align to see things because thus far I have seen the moon and taken pictures of it, but I can't really aim it at other planets for some reason.
Yeah, which one do you have?
I don't exactly remember. It was the T something. I can go get it.
Yeah.
If you keep...
Let me ask you this: is it motorized and computerized?
No, it isn't motorized.
Oh, you
Handed.
just have to aim it.
Yeah.
Okay. So well, you should be able to see the planets with that, and it might be having to replace the. Yeah, does it have the red dot finder?
It did run out of battery because I left it on accidentally.
I'm sorry, what's that?
It most definitely ran out of battery. I left it on once, never turned it off.
Yeah. In fact, yesterday I just got a big pack of batteries that go in my red dot finder. I bought 20. I buy them like 20 or 30 at a time because they're always running out, so you got to replace them. But yeah, it's got a red dot. Usually, red dot isn't too hard to aim a Newtonian. So that's interesting that you're having trouble. So typically, going beyond the planets and finding the other objects, the dimmer objects is usually the hard part, especially in the city.
I'm not really in a city, mostly in a rural area, village-like. So I do have relatively good levels of light pollution.
Yeah.
But sometimes it's hard for some reason. Like I move it and doesn't really work with a laser pointer. So I'll try again. But yeah, if you have any tips.
Yeah, I don't know. It depends on what kind of mount does it have. Does it have the altazimuth mount? Goes up and down and sideways?
The mount, I think it's similar to one of them in the picture right now. On the top right, the next one. Yeah, it's this one, but without the mechanized parts. It does have mechanical on it.
Okay, so it's what's called an equatorial mount. So
Yeah, an equatorial.
okay, there's your problem. That is actually hard to aim, yes, because the axes don't behave the way you expect them to. So yes, it definitely is a little tougher to aim those, especially at dimmer objects. But the other problem we have right now is there aren't many planets out there. Venus, and that's pretty much it in the evening sky. About midnight, Saturn comes up in the east. So, but have you been able to look at Venus?
Venus, no, I don't think. But here in Greece, I think Jupiter is also up.
Well, Jupiter is really low to the horizon now.
Yeah, sometimes I see with my naked eye, and it's like 20 degrees above horizon, 30 at most.
Yeah.
Yeah,
So,
and it's on the side of a mountain, so it's kind of hard.
yeah, in general, what you want to do is release the clutches a little bit on those axes and just keep them just barely tight enough that it doesn't droop. The scope just doesn't go by itself. And that way you can kind of turn it in both directions at the same time. But you're right, because it's an equatorial, it's a lot harder to aim. That's true. And I would just continue practicing with it. Try Venus. The other thing is to be sure that the red dot finder is aligned with the telescope.
Okay.
So there are two knobs on the red dot finder. Let me go back to this picture and see if I can see them in this picture. Where was that? Yeah. There's this knob in the back, moves the red dot finder up and down, and this knob right here on the side of the front moves it back and forth. So what I do is set up in the day and aim as something as far away as you can see, like the top of a telephone pole or something, or a power pole. or radio station tower or something way off as far as you can get it lined up in your telescope, and then adjust these knobs on your red dot finder until it's centered on whatever you're looking at.
Okay, thank you. Because I did read the instructions, but I never got how to actually align the whole thing. Like I
Right,
was
right.
doing this, and I saw almost nothing happened, and like,
Yeah. Well, that's the way I do it. So I do it during the day and make sure that your red dot is aligned. If it's not aligned, that doesn't help you a lot. That's the other problem, especially on the planet. You can be a little off on it. The moon is okay because it's bright enough. You just get close, you can see it. But on the planet, you need that red dot pretty much aligned.
okay, okay, perfect, thank you.
Okay. Where do you live?
In northern Greece.
Oh, okay. You live in Dallas, I can help you. Northern Greece. Yeah, that's a
Yeah,
little.
wait.
But the other thing is, if there's a astronomy club nearby, look for one, and they can help as well. So
Yeah, I'm actually in a relatively remote region. I haven't found people with similar interests, but
okay,
yeah, in a year I'll go to university. I'll find someone there,
yeah,
probably.
yeah. Well, try adjusting that red dot finder. Look online for how to align it. But once again, I do mine during the day on a building or something way far away, and get them to align, and that'll make things a lot better. Okay.
Okay, okay.
Well, good luck.
Thank you.
All right. Any other questions? Okay, Tyler, I'm going to turn it back over to you. And once again, Tyler will be posting this later. So
Yeah, I'll be posting this later. So what's next is that we'll give a short talk about what we are because we haven't done that yet. So yeah. So me and Hanson made this presentation. So this is what the Texas Astronomical Society of Dallas is. So TAS, or the Texas Astronomical Society of Dallas, is an organization that's based in Texas that features monthly meetings at the University of Texas at Dallas. It also has a dark site in Oklahoma that's free to its members. So that's that. We also have a dark site over here, which is free to anybody that pays the membership fee, but we'll get to that later. So we have two groups that we have. Well, two groups of tasks, or the two youth groups. So we have a younger group, which is JTAS, which is first to seventh grade, 7 to 12 years old. And then we have TTAS, which is the older group, which has people from 8th to 12th grade. So TAS membership is required to join JTAS/TTAS. Other than that, no real prerequisites are needed besides age. So what do T-TAS and J-TAS usually do? So J-TAS is mainly for children to learn about the stars, have fun, and learn how to use telescopes. Though if you already know all of that, you can do research or present at meetings like Shri or Olivia do. Other than that, T-TAS is where are able to be able to get into research, present at meetings, and get into physics stuff. Also, T-TAS and J-TAS are now getting a $40,000 remote research observatory for use by any member, though we still need to put the roof on. So this is how you join J-TAS and T-TAS. So there's a $60 membership fee. Is that right, Kevin? Or
yeah, it's $60 for the first member, and then $5, I think, still for each additional family.
okay, so it's like $60 for your parents and then like $5 for anybody else. So here's the link to the TAS membership portal. All you need to do is fill all the information here. And then here's the link to the Google form in order to put on the registration list. Besides that, me and Hanson are looking into this because this camp features international people. Me and Hanson are making a sort of community to help you start astronomy clubs or help find people that have interests. We're gonna also help find speakers for this. Though we just created this a week ago, it's like relatively new. So yeah. Anyways, that's what we are, and yeah. So the next presentation up is still by me. It's going to be the bizarre stellar graveyard. Oh yeah, does anybody have any questions? Oh yeah, sure, I can post it right now. I'll also be sending this all in an email at the end of camp or Friday. Yeah, that's that, and that. I'll present this tomorrow again because there's only 20-ish people online when there's 40 before. So yeah, in case if they didn't get the information. So I'll go ahead and present this presentation next. Okay, so now we're going to be talking about the bizarre stellar graveyard. This presentation is mostly about neutron stars and other stuff, like white dwarfs. So let's go ahead and get into it. So here's some questions for you guys. What is a white dwarf? Does nobody know?
Forms after a star dies, something like that.
Kind of. Is there any better answers? Oh, George?
It's like it's like one of the stages of a star.
That's true. George?
I think it's the core of a star that basically went through the red giant phase and had its outer membrane completely removed, to say, reflected from the core and then expelled into the rest of the solar system.
That's correct. Kevin, did you have to say something?
Oh, I'm sorry.
Oh, what can happen to a white dwarf in a close binary system? Actually, do any of you know what a close binary system is?
No.
No.
Okay, that's fine. We'll get into this later. So we've already asked, what is a white dwarf? So white dwarfs are the remaining cores of dead stars, and electron degeneracy pressure supports them against gravity. Does anybody know what electron degeneracy pressure is?
No.
So electron degeneracy pressure is basically a quantum mechanical thing, assuming that no two same electrons can occupy the same space at one time. So basically, when gravity goes to a certain point, electrons go to a higher energy state. So electrons go into a higher energy state, meaning that they move more violently. So yeah, that's what electron degeneracy pressure is. So white dwarfs cool off over time and grow dimmer. Does anybody know what this graph is?
I think
George?
stages of
Hertzsprung-Russell. Is it a Hertzsprung-Russell diagram?
That's true. That's correct. Good
is it
job,
a
Shri.
stage of a star? Like the stages?
Is it like the graph? Like
No,
where
it's
you
it's
just
like a
looking at
graph
the
of
shape of
all the stars
like
and what
the
stage they're in.
how bright the star is and how like
It
how
which graph
hot it is.
Yeah, which stage they're in.
That's all true. So the correct term, like Shri said, is the Hertzsprung's Russell diagram. So let's go into the next part. So white dwarfs are almost have the same mass as the sun and are about the same size of Earth. Higher mass white dwarfs are also smaller, if you didn't know that. So what this means is that one mass is one mass of the sun, 1.3 is 1.3 masses of suns, so think about 1.3 suns. So the white dwarf limit is something that we're going to talk about, also known as the Chandrasekhar limit. So quantum mechanics, like I stated before, says that electrons must move faster as they are squeezed to a smaller space because they cannot occupy the same space at the same time. So as a white dwarf's mass approaches 1.4 suns, electrons must move nearly at the speed of light. And because nothing can theoretically move faster than light, a white dwarf cannot be more massive than 1.4 suns. Well, cannot contain more mass than 1.4 suns. And this is known as the white dwarf limit. So this is back to our question about what can happen to a white dwarf system in a closed binary system. So what do you guys think now?
Basically, it kind of blows up.
Kind of.
Becomes nova, like it just brightens.
Kind of. Does anybody know the difference between nova and supernovae?
Supernovae are like basically the star just completely explodes, whereas a nova is like I think like just a flash and then send out a layer of matter.
That's true. So stars that started with less mass gains mass from its companions. This is what happens in a binary system. So after this happens, the white dwarf slowly gains more
You can
mass.
call this like a type 1A supernova sometimes.
That is the exact term for it. How did you know?
Stuff.
Are you using a special search engine called Google?
Maybe.
Okay. So eventually the white dwarf mass will steal stuff from the losing star because it has an outrageously strong gravitational pull. So this creates an accretion disk. And when stars have an accretion disk, they naturally rotate faster due to angular momentum. So how is this important? So the more mass that it is formed because of accretion disk, because it's moving so fast and the white dwarf is rotating at a faster and faster speed, this will eventually cause a nova or nuclear fission that will happen due to the material from the star being heated up to millions and millions of degrees. So nova is basically what I just said. The accreted mass becomes too hot and causes hydrogen fusion. Fusion begins suddenly and exploding, causing nova or a bright flash of light, as Alexander said before, totally not using Google. So nova
Using Google.
Okay. So nova is when a star system appears temporarily brighter because of a bright blast or hydrogen fusion. So the explosion drives a lot of matter in space, but it doesn't destroy the white dwarf. So there are two types of supernova. So this is when a massive star reaches the limit, the white dwarf limit, and collapses into a neutron star. And then there's a white dwarf supernovas when so supernova basically is when a star completely destroys itself. That's all you really know. And then there's like a big star, and then there's a white dwarf. So massive supernova, this is like how bright one is. So one way to tell supernova types is by light curves. You can use this using tests, a software. So nova or supernova. So supernovae are much more luminous. Does anybody know what a supernovae is?
So basically, like you have this really large old star that blows up. Because like basically it starts trying to fuse iron towards the end of its life, and then you can't really fuse iron to produce energy. So in the balance, like basically fusion would have created a balance between the gravity that pulls the star inward. So then the star basically just in the end explodes.
That's true again, Alex. Surprised you're the only one answering my questions.
We wonder why.
So supernova types, the main difference is light curves, and that's they don't usually destroy themselves. So this is what we've learned so far. We'll post this later if you guys want to read this. So now we'll be going on to neutron stars. So what's our most important question so far? What is a neutron star? Can anybody answer that? Anybody but Alex, please.
All right, fine.
Will.
Go ahead, William.
A neutron star is the result of a supernova of a massive star, and that didn't pass the limit for becoming a black hole. And so it's mainly composed of neutrons. It's a neutron soup, and it's also super dense.
I think it's the collapsed core of a supernova.
Okay, so now we'll go on to how are neutron stars discovered. Okay. So does anybody want to do this? Answer this question? Are you guys... Oh, George?
Hi. This is just a guess, but I think it was from radio waves that were hit from them. Or is that the process?
That is correct.
Oh, okay.
So, what can happen to a neutron star in a close binary system?
Basically, they collide.
Kind of true. They
apparently like they can either explode. Like basically, it sends like out gravitational waves if the neutron stars are big enough.
Yeah.
Kind of.
If they collide, apparently sometimes it makes a black hole.
So, George, do you have anything else that you want to say, or?
I did hear about the magnetar term once, but I don't know if it's if it relates to anything. Like if two neutron stars collide, it can become a magnet star, something like that.
Well, the one part that you guys all missed was that it can also form an accretion disk too. So, what is a neutron star? So, a neutron star is a ball of neutrons left behind by either a massive star supernova or a white dwarf collapsing. So, degeneracy pressure of neutrons support a neutron star against gravity. Basically, what I said before. Does anybody remember what degeneracy pressure of neutrons is? Come on, guys, this cannot be that hard. George.
Is that the thing we said before about how two electrons can be in the same level? Or
That's
am I mistaken?
absolutely correct.
Oh. The mic is muted.
Oh, my bad. So electron degeneracy pressure goes away because electrons combine with protons, making neutrons and neutrinos. So neutrons collapse to a center, forming a neutron star. Basically, why neutron stars are called neutron stars are because they consist of neutrons. So, oh. Forgive the lag right now. My computer's a bit slow today. Also, Kevin posted a link in the chat. If you guys want to, you guys can go ahead and check it out. So basically, what's the next slide saying, if I could get it to load, is that neutron stars can be the size of a city and are relatively small compared to your normal planet or star. So, how were neutron stars discovered? Kevin's article kind of talks about this, but it was because that neutron stars are also pulsars and they have periodic blasts. So, using a radio telescope, Jocelyn Bell noted regular pulses of radio emission coming from a single part of the sky. These pulses were coming from the spinning neutron star, or known as a pulsar.
Real quick, Jocelyn Bell was a grad student at the time and discovered him. Her advisor, her professor, won the Nobel Prize for that. She did not. A few years ago, though, they did give her the equivalent of money for the Nobel Prize for a discovery, which she donated to help women in astronomy.
That is correct. Thank you, Kevin. So pulsars also happen at the center of the Crab Nebula, which pulses about 30 times per second, which you can see right here. This is the map of that. So there are two types of pulses. There's one that we can see that are visible with light, and those are X-rays. So the reason why pulsars happen is that because the magnetic field is not aligned to the axis of rotation. So every time it misaligns, there's a curve, it blasts out lots of material. Hence why you see pulsars rotating like this in the beam, being not in one direction at a time. Kind of like our Earth's axic, how it's rotated on a point, but the magnetic field is off. So pulsars are giant radiation beams that sweep through space like a lighthouse. And this is why pulsars must be neutron stars, because the spin rate of fast pulsars overcomes anything else, because by spinning out that much material, it needs to be this fast. So if you guys want to look at the math, you guys can do that yourself. I'm not going to explain that. So pulsars spin fast because of core speed. It's up as it collapses into a neutron star. This is the conservation of angular momentum. Does anybody know what this is at all? This is physics. George?
So basically, we already have conservation of momentum for linear. Basically, what we have for conservation of angular momentum is a parallel of the linear momentum stuff.
That's correct, Alex. How about you, George?
Yeah, pretty much the same thing because the star was rotating. When it when it became a neutron star, the momentum couldn't disappear because then energy would just be destroyed, and thus it continued spinning.
That is correct, George. So next slide. So what can happen to a neutron star in a closed binary system? This is basically just a high amount of mass that's gained in a short period of time due to an accretion disk. So matter falling towards a neutron star forms an accretion disk, just as in a Wipf binary. The accreting matter adds an angular momentum to the neutron star, increasing its rate of spin. So this
But what happens if I add like so much matter that the neutron star becomes like 1.5 solar masses?
It will still be fine. 1.5 is fine for neutron stars.
Sure.
1.5 is not fine for white dwarfs. When it goes to above 1.4, it will collapse into a neutron star or have a nova explosion. So episodes of fusion lead to giant blasts that we talked about before in pulsars. So matter accreting onto a neutron star can eventually become hot enough for helium fusion, which creates giant X-rays. So this is what we've learned so far. Does anybody have any questions? No questions? Okay, then I'll keep going then. So this is also what we have learned. Still no questions or okay, then we'll talk about black holes next. So our first question for this short lesson is what is a black hole? Who can answer this? Should be an easy question for you guys.
Basically, just a singularity.
That is true, Alex. George?
Yeah, a place where gravity is so strong that not even light can escape.
That is true. William?
A place where there's like infinite gravity, not even light can escape it.
Also good. Eddie?
What?
You opened your mic earlier, like you were gonna answer, but you got cut off.
Nah.
Okay. Then what would it be like to visit a black hole?
It would not be very healthy.
That is true.
Say
Very
goodbye.
Basically, you turn into spaghetti,
true.
which is then pulled into subatomic spaghetti, etc.
That is true too, Rob. George?
Yeah, he isn't wrong, but I did hear that if you go into a supermassive black hole, the spaghettification effect doesn't really happen. Instead, you just see the world go around you slowly, slower, as you reach the black hole because higher gravity,
Heard you
the
just see
time
the
passes
entire
slower.
future of the universe in like 0 time.
Huh? I didn't hear.
Like theoretically, you see like the entire future of the universe in 0 seconds.
Okay. Alex? All very good points. And the biggest question, do black holes really exist? We kind of know that they do. Yeah. So what is a black hole? We already know about that. This is a Google definition. So in order to escape a black hole, you need to have a lot of math. So this is all the math behind that stuff if you guys want to look into it. So light would also not be able to escape Earth if it was shrunk to 1 centimeter. I could probably find this simulation later for you guys if you guys want this. So the surface area of a black hole is the radius at which the escape velocity equals the speed of light. The spherical surface is known as the event horizon, and the radius of the horizon is known as the Schwarzschild radius.
It's
Forgive me if I pronounce that wrong.
Schwarzschild. Schwarzschild.
Nice. The Schwarzschild.
Schwarzschild. It's German, I'm pretty sure.
It's Schwarzenegger's cat.
Forgive my mispronunciation.
Schwarzschild radius.
It's Schwarzschild radius.
So okay, now it's not glitching. So the event horizon of a Ethereum black hole is also the size of a black hole. So something that I didn't talk about before is that when a neutron star reaches a mass of 3 suns, it will collapse into a black hole. So yeah. So this is all glitching, so forget this. So the event horizon is bigger for black holes of a larger mass, something you guys all know. So, and a black hole mass strongly warps space and time and vicinity of the event horizon. So nothing can escape from the event horizon. You guys all know this already. And the neutron star limit, which I talked about a bit before, is that neutron degeneracy pressure, where that neutrons cannot be in the same space, only is able to be supported if a neutron star is able to.
Wait,
Yes,
so what
Alex?
if I like start pouring in a whole lot of matter into the neutron star
Do you
until it
have?
reaches like 3 solar masses?
If you have 3 solar masses, it will just collapse or explode into a black hole. Well, it depends on the conditions. And then some supermassive stars can also collapse into a black hole if enough mass falls on the core. Mainly, it's just how much mass will actually hit the core in order for it to fully collapse. So beyond the singularity, it's when a neutron star collapses is just a singularity or a black hole. So, what would it be like to visit a black hole? Most of you have already answered this before.
Die.
Yes, die. So, if the sun struck into a black hole, its gravity would be different only near the event horizon because it's slow. And black holes don't suck, its gravity pulls. Does anybody know what redshift means?
I do.
I
The
forgot.
apparent change
The
in
fa-
I
wavelengths.
forgot.
the faster
I
an object is moving away from you, the more red it seems.
Yeah, so basically it's kind of a Doppler effect, but for light.
True.
I love. George, your answer?
Yeah, because light is a wave, when something moves further away from you and emit photons, it gets more stretched out, and thus the frequency becomes smaller, and you can see it more on the red. And the opposite is when something is moving towards you, it becomes more blue.
That is correct. So time slowly passes near the event horizon, something you guys all have stated before, and tidal forces near the event horizon of three massive suns would be lethal to humans. But tidal forces that were stated before by Alex or Shri would be gentler near a supermassive black hole because it's much bigger in radius. So three solar masses black hole is basically how much mass you need for a black hole to form. And this is all information on do black holes really exist, black hole verification, anything that extremes sees three solar masses is a singularity, also known as a black hole. So this is more stuff. This is some neutron stars or X-ray binaries are able to exceed three masses because they are able to eject enough stuff. One famous X-ray binary or neutron star with a likely black hole is the constellation Cygnus. This is all that we've talked about. Yeah, not much else. Next star, the mystery of gamma ray bursts. So, where do gamma ray bursts come from? And Alex, no searching this up on Google.
I went to searching.
George?
In a black hole, in the accretion disk, when a lot of material gathers, it gets real fast, and that can result in it melting and releasing a gamma ray burst, if I remember correctly.
That is kind of correct. Does anybody else have an answer? Really? So,
They come from gamma radiation. Right?
kind of. It's why they're called gamma ray bursts. They consist
Bro.
of gamma or just a radiation in general. How about what causes gamma ray bursts?
Gamma decay? I don't know.
Nobody? Does anybody else have an answer? Okay, then I'll talk about it in the next few slides. So, where do gamma rays come from? So, gamma ray bursts were first discovered in the 1960s. This is all the graphs that showed that they used. So, observations in the 1990s showed that many gamma rays were coming from very distant galaxies. They must be coming from one of the most powerful formations. So, basically, what a gamma ray thing is that gamma ray burst is that it's a giant flash of light that is caused by either a massive collapse or a merging of two different objects. Like, for example, neutron stars smacking against neutron stars, or neutron stars smacking against a black hole. So that's what that is. So what causes gamma ray bursts? Like I said before, supernova, the collapsing of a massive star can cause it, and collisions between neutron stars can also cause that too. So what have we learned? Where do most gamma ray bursts come from, and what causes gamma ray bursts? So that is the end of this presentation. Now I'll put on a blanket.
No.
I can find a game kit after.
No.
And maybe a Kahoot.
Yeah, game kit.
I need to find one though, which is the problem. I'll find one later for you guys. Okay, so what game mode do you guys want? Or who won the who won the thing on Tuesday?
Well, we need to ask that. So,
What,
Monster
William?
Brawl?
Monster Ball?
no,
What do you want, William?
I don't know. What should I get? Oh,
Please choose gold quest or
Snowy
something.
survival.
We're not doing
it's
a
not
game
game
kit.
kit.
Fish Frenzy?
Yeah, do fishing frenzy or gold
Yeah.
Yeah,
quest.
Fish Frenzy.
Okay, fishing.
All right.
Let's do fishing
Wait,
frenzy.
what about cafe?
Can you give me a
No,
link?
no, cafe's too, like,
Chill.
yeah, sounds like chill.
Can you give me a link?
We're not done setting it up yet.
Okay, so do you guys want your 10-second penalty or no?
No, no, three. Three.
Three
Set it to three.
seconds.
Set it
Bro,
to
what
three.
were you thinking?
3 seconds. 3 seconds.
Okay, so that's this. They'll be posted in the chat.
Rob, do you want another shot?
Bro, who named themselves Eddie Lee? Will, is that you?
Uh,
Bro, Will,
I
that's
thought
gotta
that
be
was you.
you. Will, that has to be you, bro.
No, it's probably the strat, whoever that was, because they were talking about like a strat, whatever.
I think that's
Oh,
Will.
no, the strat was me, but like, who's Eddie
And that,
Lee?
I'm 99% sure that's not Will.
Rob,
now I
do
don't
you want
think
another
it's you.
shot though? Do you want another shot?
Yeah, I want to know the strat.
Oh, okay. Okay.
Okay, we'll be starting now. Yeah.
Boo.
If you haven't joined yet, tell me now. You have 5.
Boo.
Okay. 5, 4, 3, 2, 1. And now we're starting.
Please mute him. Please mute it.
I'm
Mute
giving you
Eddie.
some inspirational music.
I'm selling.
Distractions are so bad. Next time we should remove them.
What?
I don't think.